Morning, everyone. On behalf of the Department of Physics, first of all, am I audible?
You are.
Yes, you are.
Good morning, everyone. On behalf of the Department of Physics of Adams University, it is my great pleasure to welcome you all to the third National Conference on the Frontiers of Modern Physics. First of all, I would like to extend our warm greetings to all the participants here from our department. As you might know, this is the annual conference series that we organize from the Department of Physics of Adams University, and the present conference is the third one in that series. The objective of this conference is to bring the scientists, researchers, and academicians working in the field of physical sciences on a call to discuss and exchange ideas on their recent findings that have been in the past. I sincerely hope that with your active participation, this objective will be achieved. Before I turn over the conference to the chairman of the first session, I would like to wish you a delightful and very engaging conference ahead. Now, at this stage, I would like to, it's my pleasure to introduce Dr. Moumita De, who is the associate professor and head of the Department of Physics of Adams University. Dr. De did his graduation and post-graduation from Calcutta University and did her PhD from the Saha Institute of Nuclear Physics, Kolkata. Her research interest is in the theoretical condensed matter physics and speed learning. It is my great pleasure to welcome Dr. De, and I request Dr. De to take over from here. Thank you. Thank you. Dr. De, please.
Thank you, Dr. Mukherjee. Am I audible?
Yes.
Am I audible clearly?
Yeah.
Yeah. Honorable Pro Vice Chancellor, Academic Affairs and Dean School of Business and Economics, Professor Naveen Das. Honorable Pro Vice Chancellor, R&D Affairs and Dean School of Basic and Applied Sciences, Professor Jeetendra Pandey. Respected Dean R&D Affairs, Professor Moumita Mukherjee. Convener, Professor Bimal Kumar Sarkar. Our esteemed speakers, my dear colleagues, scholars, and students. A very good morning to all of you. I'm really delighted to say that this is the third time we are organizing this national conference on frontiers in modern physics, which started in 2018, aka NCFMP 2021 this time. Had it been an offline conference, we'd be more than happy to host it. However, we will have to accept, but we can't change. So, and we must try to deliver the best, to try for the best, and hence the online mode. I believe it's a trend more likely to continue even after the pandemic, and because researchers are now increasingly trying to accept the new virtual reality of scientific gatherings for various reasons. So I hope with such an esteemed and distinguished panel of speakers, NCFMP 2021 will be a great learning opportunity for all of us. And with this ambitious note, I'd like to request our Pro Vice Chancellor, Sir, Dr. Naveen Das, for the welcome address. Dr. Das has a perfect blend of academic and corporate experience, having done his BTech from IIT Kharagpur, PGDM from IIM Calcutta, and PhD from NLU Jodhpur. In his almost a decade of corporate experience, he has held positions like SBU head in Godrej & Boyce, Kolkata, Vice President in Intellectual Capital at F1 Education Systems, Chennai, etc. In his academic experience spanning more than 2 decades, he has held positions like Founding Dean and Director, IBS Business School at both Hyderabad and Kolkata, and as Director, School of Business and Management, NSHM Knowledge Campus. So thank you so much, sir, for joining us. Now I would like to request for the welcome address. Over to you, sir.
Thank you, ma'am. Good morning, all my respected colleagues, seniors, particularly Professor Sarkar, Professor Ghosh, my dear colleagues, Professor Pandey, and everybody who is there on the platform today, participants from within Adams University, as well as outside Adamas University, dear students. I think in the life of an academic, whether as a teacher or as a student, this day doesn't come every day, that you will listen to a person of the stature of Dr. Sinha. Padma Bhushan, Padma Shri, Professor Vikas Sinha. He is an institution by himself. I'm sure when Professor J.K. Pandey asked the question as to how many of you have heard about him, I'm sure almost everybody must have gone to Google and searched his profile. By now, you must be knowing that he is a doyen of nuclear physics in India, perhaps a living legend. So this day doesn't come every day in the life of an academic. So we are really fortunate, all the organizers who have helped to have this day realized. It's also my pleasure to welcome the other speakers, again stalwarts like Professor Amitav Rai Chaudhuri, Professor Anup Kumar Rai Chaudhuri, Professor Shourabh Basu, Professor Sandeep Chakraborty, Professor Dev Narayan Jana, Professor Chittaranjan Sinha, and Dr. Barnali Ghosh to today's program. I'm very, very hopeful that this kind of program is in line with our university's overall overarching goal of making knowledge boundaryless. In fact, not only in physics, almost in every field, the frontiers are breaking. We are seeing social sciences getting into physical sciences and vice versa. In fact, the latest issue of Scientific American talks about, in quite a few articles, talks about these boundaries breaking up. They say that Industry 4.0 vis-a-vis Industry 3.0, perhaps the greatest difference is that here, man, machine are almost integrated. It is neither the machine controlling the man or the man controlling the machine. They work in tandem, as if the frontiers between the living and the non-living have merged. And I think with these thoughts, I'm sure the organizers have organized this beautiful symposium, beautiful seminar, beautiful conference, whatever you call it. And with such speakers on the platform today, I think at the end of the program, it will be very, very enriching to say the least. And I think many of us, we are going to take away points from here to see where we are heading towards in the days to come, in the decades to come. Obviously, I have read the short introduction to the program. People say that science precedes technology. By training, by profession, I am a technologist turned management graduate or management professional. And obviously, I had my +2 in science, so I could relate how a scientific mind can give rise to technology. And we all know when you harness the advantages of science through technology, it becomes beneficial to mankind. But I think sessions like today's, I'm sure are going to force us to think beyond on both sides. Perhaps to give rise to science, the curiosity of the mind, the questioning. Sometimes on a lighter mode, we say that those 5 good serving men of Rudyard Kipling is necessary. In fact, all those 5 serving men are necessary for making this mind curious. And it is the curious mind which is a beautiful mind. And it is the beautiful mind which gives rise to science. And it is science that gives birth to technology. But beyond technology, I think all the participants here, particularly my dear students, please remember, at the end of your studies, at the end of whatever you are going to do in your job, in your research, if it doesn't benefit human beings, finally it comes to a big knot. In fact, the life of people like Dr. Sinha actually illustrates this phenomena very, 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 very deeply and evidently. A man of science, a man of thought, but more importantly, he has built institutions. I don't think it would be far-fetched to compare him almost like Sir J.C. Bose. Such a brilliant mind, such a brilliant scientist, but at the same time, an institution builder. And some of his institutions are still there for all of us to visit and see. So without much ado, waiting agog to hear him, I once again thank all of you to come onto this platform on this beautiful morning, gathered here to listen to the stalwarts and take a day out learning and thinking about humankind. Thank you very much, ma'am, and over back to you.
Thank you very much, sir. Thank you, sir. And I have seen Professor Sinha has already joined us. Thank you, sir, for joining us. A very good morning and warm welcome. And now I'd like to request our Pro Vice Chancellor, R&D Affairs, Professor Jeetendra K. Pandey, to say a few words. Professor Pandey completed his PhD from National Chemical Laboratory, Pune. His research areas are bio-nanocomposites, degradation and stabilization of polymer composites, nanomaterials for water treatment, etc. He has got 70 plus research articles, 6 books, and 17 patents to his credit. He was associated with the research and development wing of University of Petroleum and Energy Studies, Dehradun, Seoul National University, South Korea, the University of Tokushima, Japan, Max Planck Institute of Colloid and Interfaces, Germany, in various roles prior joining Admas University. Thank you, sir. So now over to you. Please say a few words.
Thank you, Dr. Day, and thank you, Das sir. Good morning, everyone. I could see Sinha sir was here, and he, I think, is still with us. His video is switched off. Sir, good morning. Hope you are. I mean, we all are audible to you. So maybe we can just send a message to him, right? So in continuation of Das sir, and I formally welcome each and every participant of this conference. Welcome my dear colleagues, Dean School of Media, Professor Mahul Brahma, Dean School of Law, Dr. Ashish Verma, our guardians and mentor, Professor Sanjeev Bose, Dr. Bimal Kumar Sarkar, who is still our colleague and who will remain our colleague, Mamita Day and Dr. Mamita Mukherjee, Aparajita ma'am, thank you for helping us for this conference. So in continuation of what Das sir said, there is no doubt we are blessed, we are thankful of time by Professor Vikas Sinha and other speakers for sharing his thoughts mainly with our students. Sir, Admas University is comparatively a new university. It is under the umbrella of Sakshi Kiran Roy Memorial Trust. We were established in 2014. We have a campus of nearly 120 acres, with facilities of say around 1,200 students inside the campus, and around 60 plus faculties are at present residing inside the campus, and we are having a plan to go for a 24/7 campus. We have 10 schools, ranging from media and communication, law and justice, engineering, education, basic and applied science, pharmacy, life and biotech, School of Life Science and Biotechnology, School of Business and Economics. Nearly 250 plus faculty members, 5,000 students, and around 60% of our faculty members are PhD. Faculty members who are working in science domains, they are nearly 100% faculties are PhD. We have well-established facilities, sir. Although we are young, but we are able to develop a fully fledged studio, media studio. We have a central instrumentation center uh, uh, where most of the sophisticated instruments are under one roof. We have nearly 44 plus high-end instrumentation centers. Those are open not only for faculty members, but for postgraduate students. We have dedicated international cell, nearly 50 plus functional MOUs. We have dedicated center for career development of students, where the overall personality development training is being given to all students. Recently, we have established a center for lifelong learning to establish a kind of harmony with the existence. As Tagore has said, that education is not merely information. So this Center for Lifelong Learning will be having various responsibilities. So one of the major responsibility is what one can give other than information. In terms of research, sir, we have been receiving funds from DRDO, fund from Department of Science and Technology, Department of Biotechnology. We are certified research center by DST and Government of India. We have been receiving funds from couple of industries, and in terms of having number of publications, recently we crossed 1,000 plus quality publications. And when I say quality, so this is only Scopus and SCI Impact Factor journals. Two of our faculty members were featured in top 2% of the scientists by Stanford University recently. Research is not being driven only by faculty members. We have a very good facility, a center or system where students can take part actively in the research. We have financial support that is called ARISE. So any student can apply for this financial support. We have a plan of IDP, interdisciplinary projects where students are directly involved. We are running a scheme that is called dissertation to publication. So any student, if he gets published their major or minor thesis, then he gets recognized. We are still coming up, sir. We feel that we are still in our budding state, and we are trying to get blessings and support from various scientists around the world. We were fortunate enough to host 3 Nobel laureates as a special lecture as well as for our communication. And we have been regularly organizing various conferences throughout the university. So, sir, thank you very much for your time. And once things get normalized, I welcome each and every participant, especially Sinha, sir, to please take out some time. This is an advance invitation from my end that you will visit us physically and you will interact with our students. We have nearly 1,200 species of plants in our campus, and around 100 types of birds are here. We would be very happy to have you in the campus, sir. Definitely, this conference was conceptualized long back. This is third in a series. I am thankful of Dr. Bimal Sarkar, who have been working for this conference since long. Dr. Momita Day and all other participants. As I said initially, Dr. Bhattacharya, Purva, Shatrupa, Deepsikha, they all have been working. And we were always talking that had it been a physical conference, a face-to-face conference, so this would have been given a different type of energy to us. Our student would have interacted with each one of you. But anyway, we hope that situation gets fine, and by the time we reach to the fourth edition of this conference, we will be having offline conference. For this fourth edition, we have, sir, collaboration with the IOP journal, with the Scopus Index journal. So hopefully, some of the proceedings and full paper will get after a peer review will get published into that. So, sir, thank you so much once again, and looking forward for 2 days full of knowledge with fun, with the interacting sessions. And I request all the participants, if they want to ask anything to Sinha sir, they are most welcome. They can always write into the chat box. So thank you so much, everyone.
Thank you so much, sir, for this nice introduction about our university, our school, and our department. And now I'd like to request our Dean, respected Dean, R&D Affairs, Professor Moumita Mukherjee, to introduce the participants about our Department of Physics and its research activities and different other activities, and School of Basic and Applied Sciences a little bit. Dr. Moumita Mukherjee, an alumni of Presidency College and Calcutta University, did her PhD in radio physics and electronics from University of Calcutta. She received visiting scientist and postdoc positions in Newcastle University, UK, and Technical University, Darmstadt, Germany. Dr. Mukherjee was attached with DRDO Center under Ministry of Defense, Government of India as scientist. She has guided more than 35 postgraduate theses and 12 PhD theses as supervisor and co-supervisor. Her research interest is focused on terahertz electronics, semiconductor devices, graphene electronics, photosensors, nanobiosensors, and medical electronics and instrumentation. She has published more than 150 research articles. She is principal investigator of 5 government and industry funded projects as well, of around 60 lakh watt. So over to you, ma'am. Thank you for joining.
Thank you, Dr. De. Very good morning to everyone. Honorable Vice Chancellor, Pro Vice Chancellors, Dean School of Basic and Applied Sciences, Head of the Department of Physics, and all eminent dignitaries, professors, scientists, and conference participants from different parts of India and world. It is indeed our great pleasure to welcome you in the 3rd National Conference on Frontiers in Modern Physics. Before the commencement of the conference, let us have a brief review about the Department of Physics, which is a part of School of Basic and Applied Sciences. Now, as Dr. Pandey has rightly explained, Adamas University wishes to establish itself as one of the frontiers research university in India. And in order to fulfill this mission, we have already taken various schemes and for the implementation of and to encourage and promote culture of research and innovation amongst the faculty members. So Department of Physics started its journey in 2015, and we started our journey with 2 programs initially: undergraduate program BSc Physics and postgraduate program MSc. Now, with the overwhelming response of students, we introduced later a new program, Applied Physics domain, namely Medical Physics and Instrumentation. Now, our undergraduate and postgraduate laboratory infrastructure are rich enough, and that is comparable to any frontline university in India. In this short period of time of 5 to 6 years, we have established that. We have dedicated advanced mechanics lab, laser and fiber optics laboratory, thin film lab, then biomedical instrument lab, semiconductor device lab, advanced electronics and microprocessor laboratory, biophysics laboratory, condensed matter physics lab, and high-tech modern equipment facilities. So the department conducts research in frontiers areas as a part of the undergraduate, postgraduate, and doctoral program. The research program of the department cover both pure and applied physics. That area includes condensed matter, particle physics, theoretical nanoscience, material science, plasma physics, microelectronics, biomedical instrumentation, and electronics, thin film and biophysics as well. So we have PhD students who are conducting research in these areas. Faculty members and research scholars are regularly publishing good research papers in internationally reputed journals, and till date, on record, we have published more than 150 peer-reviewed research journal papers in reputed journals and got citation globally. Those prestigious journals include Nature's Scientific Reports, Physical Review, IEEE Transactions, and many more. Our departmental H index presently is 10, and that too in just few years. Faculty members of the department have already published 2 patents and granted 1 for their research in the field of smart UV sanitizer development and artificial intelligence-enabled CT scan-based early COVID detection. This is a path-breaking work that we have done for the benefit of mankind, and students are doing hard work for its development. We are proud to inform that within just 5 years of our journey, we have received more than 1 crore of extramural research grant from DST, ACRB, DRDO, government sectors, as well as industry, and as well as various industries under the Department of Physics. Our students have received many prestigious awards from DST, IEEE in recent times. We are conducting 2 conferences annually, including this one in CFMP, and another one we are conducting in the field of advanced physics, namely advances in medical physics and healthcare engineering. And we have received attention of several scientists and researchers all over the world for these 2 conferences. We are proud to inform that our students have got placement very successfully in recent years. And physics pass out students have received prestigious doctoral fellowship from universities of Germany in UK in recent times. So with this, I will conclude here, and I hope in these 2 days of conference, participants will gather vivid knowledge and get enriched. All my good wishes and success for the 2 days meet. Thank you.
Thank you so much, ma'am. And we have reached almost to the end of this inaugural session. And last, I'd like to request our convener, Professor Bimal Kumar Sarkar, to say a little bit about this conference. Professor Sina is already here, so let me be very brief about it. Professor Bimal Kumar Sarkar, an alumni of Jadavpur University, did his PhD from Indian Association for the Cultivation of Sciences, Kolkata, and postdoctoral research from National Sun Yat-sen University, Taiwan, and UCLA, USA. After that, he visited in research positions in many organizations like NSYSU, Taiwan, UCLA, USA, Max Planck Institute, Germany, Czech Technical University, and Slovak Technical University, etc. He has received SAIA European Fellowship and PAEU Fellowship from Taiwan. Professor Sarkar has been invited as visiting scientist in University of California, USA, and National Sun Yat-sen University, Taiwan. He is involved in the research field of material science and biophysics. Till date, he has authored 115 articles published in international peer-reviewed journals and conference proceedings. Thank you, sir, and over to you. You are mute, sir. Please unmute yourself.
Sorry. Thank you very much. So it's really very much challenging for me. I will finish within 2 minutes. Actually, we started the work for the conduction of this conference, that National Conference on Foreign Frontiers in Modern Physics. And today is the very auspicious day that we started this conference. And importantly, we are blessed by the Augusta's presence of Professor Vikas as a keynote speaker here with us. And the Department of Physics, School of Basic and Applied Sciences at Advanced University conducting this conference, which will cover many fields of physics, right from material science and then optical system, material under extreme conditions, biophysics, biomedical instrumentation, computational physics, etc. Many things covered. And in this conference, we get a overwhelming response. Many just papers, abstracts submitted. Selectively, just finally, we are able to complete the almost around 70 to 75 abstracts has been selected to be presented during these two days. And also it will be ornamented by the very renowned international renowned speakers during these 2 days. And then just it will be also very beneficial for the researchers, academicians, and not the least the students community also. And then just we will complete this 2 days session tomorrow. So then I wish all the very grand success of the conference. And now I announce the opening of the conference, the session. Thank you. Over to the organizer.
Okay, thank you. With this, we come to an end to our inaugural session. Thank you, Mohita, for conducting this.
Am I audible?
Yeah.
Yes, you are. Okay. And now I think Dr. Mukherjee, was there any network problem?
Am I audible?
Yes, now you are audible. So please continue.
One minute.
Okay.
Can I share the abstract book today, just which is to be published today? I will take only 1 minute. Please let me share. Let me allow to share.
Yes, sir.
I'm just sharing the abstract book of the conference for a moment only. Also, sir, with the permission of our today guest of honor and keynote speaker, Professor Sinha. Just we are publishing today the abstract book of the conference. I'm just sharing for a look only. This is, I think, this is the abstract book. So, altogether, the book contains 112 just pages. Start from the cover page, and then the message from the persons, and then the schedule and the abstract of the each and every speaker and also contributor today. So this is the contained 78 abstracts here, including also the abstract note of the invited speaker, keynote speaker, and then we come to the end of this abstract presentation at the end of the pages. So this is just the book of the just for this abstract. Thank you very much. Here I can now stop the share and.
Thank you, Professor Shankar.
Yes.
Yeah, thank you. So with this, we come to an end to our overall session. And thank you, Dr. Mohita, for conducting this session. It is my pleasure to request Professor Dr. Vimod Kumar Sarkar to host the second session. Professor Sarkar, please take over from here.
Yes, so now can I start the session? Hello?
Sure, sir. Sure, sir.
Okay. So it's my great pleasure and feel very honored that to just utter some word on the just about Professor Sinha to talk something. Actually, Professor Baker Sinha just started with his first-class science graduate from Calcutta University and obtained his tripos from the Cambridge University in National Science in 1967. He obtained his PhD from London University in 1970 and DSc in 1981. Professor Sinha had lived in England almost 12 years, teaching researching in Rutherford High Energy Physics Laboratory and King's College, London. Now he is with India's atomic energy establishments, now retired. He headed two institutions, famous institutions, Shah Institute of Nuclear Physics and Variable Energy Cyclotron Center. Professor Sinha, internationally known, he has traveled extensively and known to most peers of physics for Europe, USA, former USSR, and Japan. He has published more than 300 papers. The pioneering work on quark gluon plasma is well recognized internationally. He led the team from India to participate in the experiments at CERN, Geneva, as well as RHIC and DNL, USA. He, along with his colleagues, established the thermometric signals of quark gluon plasma as a definitive signal already confirmed by experiments. Recently, his breakthrough work on Hawking radiation and entropy from the relic of QCD phase transition at the primordial epoch of a few microseconds after the Big Bang, and its signatures in the universe has made a tremendous impact. Dr. Sinha joined Bhabha Atomic Research Center in 1976 after coming back from England and was appointed director of Variable Energy Cyclotron Center in 1987. He is a fellow of the prestigious Indian National Science Academy as a recognition of his outstanding research in physics, that is in 1989. He is also a fellow of the National Academy of Sciences, Allahabad. The Radiation Medicine Center in Kolkata is a part of the Cyclotron Center, also established by Professor Singh. He established the challenging project of superconducting cyclotron, radioactive ion beam source, and extremely relevant sociologically and medical cyclotron. Professor Sinha held the concurrent charge as a director, SINP, Kolkata, from 1992 to June 2009. Professor Sinha is the recipient of S.N. Bose Bart Centenary Award of the Indian Science Congress Association in 1994. Professor Sinha has been conferred Padma Shri Award by the Government of India in 2001 for his significant contribution in science and technology. He has been awarded DE Dr. Rajamanna Prize 2001 and delivered the Pandey Endowment Lecture Award IPA 2001. He is a recipient of R.N.G. Birla Memorial Award of IPA. Other recipients are Professor Abdus Salam and Professor S. Chandrasekhar, among others. Dr. Sinha was awarded Rais Ahmed Memorial Lecture Award, Aligarh 2001. He has become the fellow of the Third World Academy of Science, Italy, 2002, and Indian Academy of Science, Bangalore, 2004. Professor Sinha was Vice Chancellor of West Bengal University of Technology and from February 2003 to December 2003. Even Honorable Prime Minister of India has nominated Professor Sinha as a member of the Scientific Advisory Committee of Prime Minister from January 27, 2005. He has been re-elected for the second time as a member of the Scientific Advisory Committee to the Prime Minister from December 2009 to 2013. And he is a recipient of honoris causa DSc from National Academy of Sciences of Ukraine in 2005. Ministry of Human Resource and Development appointed Professor Sinha as the chairman of the Governing Council of National Institute of Technology, Durgapur, from June 2005 to December 2014. Recipient of numerous awards, honors. Noteworthy award are the, for example, Humboldt Research Award by the Alexander von Humboldt Foundation, Germany. In November 2005, he was awarded Professor Meghnad Shah Memorial Lecture Award 2007 from the National Academy of Science, India, in August 18, 2007. And he He has been elected as president of the Indian Physics Association on 2007 to 2010. He was awarded Magnatsha Medal of INSA 2015. And also he is appointed as a distinguished visiting scholar of Christ's College, Cambridge on March 9, 2009. He was elected to the Fellowship of Institute of Physics, London, UK in March 2009. Professor Sinha has been conferred honoris causa DSc by National Institute of Technology, Silchar in 2010, Burden University 2012, Central University 2012, NIT Agartala 13, Netish Subhash Open University 13, University of Calcutta 2014. Professor Sinha became a member of Presidency University Council 2010. And Professor Sinha has been conferred the prestigious Padma Bhushan Award by the Government of India in 2010 for his significant contribution in science and technology. Professor Sinha has become a member of the State Planning Board, Government of West Bengal, since September 2011. And he has been the holder of the Distinguished Homeopathy Chair of DE from 2009 to 2014. He has been the holder of the Distinguished Honorary Scientist position of ENSA from 15 to 19. Professor Sinha has been the chairman of both institutes councils since September 13 to 18. Professor Sinha is Indian National Science Academy's senior scientist. Sir, and finally, he recently authored a book entitled Srishti of Christi, which made an unprecedented impact on many readers. The latest book authored by Professor Sinha is Sthan Kal O Vishwalok. Sir, nicely, you have just given us a way and direction that again, with that quotation, I will finish, that you have shown us the direction, what exactly Einstein told about space, time. Sir, we are blessed by you. We feel very honored by your august presence with us. And sir, we are very happy, sir. Thank you very much. Over to organizer. Sir, now we will start the keynote speech. So now request Professor Sinha to just start the speech, sir. Over to you, sir.
Thank you very much. Can you hear me?
Yes, sir. You're audible, sir.
First of all, many congratulations for organizing this conference, which is, well, I would say very contemporarily relevant, because everybody in India is only talking about technology without bothering or worrying about the origin of the technology, which is, of course, science. A cursory glance at the conference proceedings, it seems that most of the speakers are very pointed to their subject, or very focused, shall we say. So I have decided not to be very focused as a keynote speaker, but a broad general view right from the beginning of human civilization almost on how technology has changed science over the, how science has created technology and technology evolved over the years. A lot of this technology has been used for destructive purposes, as you know. And for that, please don't blame the scientists, but the leaders and politicians and so on. So my topic today is a general one. Is microcosmos and macrocosmos from collider to cosmology. It sort of means everything, really. By microcosmos, I mean the very microscopic world of neutrons, protons, and quarks and gluons. And macrocosmos means the world and the universe that we live in. It is amazing how within that format everything happens. The abstract reads, as for conventional wisdom, I'm sorry about the printing mistake, the most elementary constituents of all matter in the universe are quarks interacting with each other by exchanging gluons. Three quarks exchanging gluons constitute the hadrons, neutrons, and protons bound by so-called strong interaction. The physics of the nucleus is referred to as nuclear physics. The universe, about a microsecond after its creation, the Big Bang, 13.8 billion years ago, must have consisted of quarks, leptons, which is electrons and muons, and the light particles. Light means alu, light particles, the photons, as per the standard model of cosmology. What is the mechanism that generates the mass of these elementary particles, and indeed the mass, therefore, of everything that we do know? And it's usually called the Higgs boson mechanism, sometimes referred to as God particle, I don't know why. And his mechanism is primarily responsible for generation of the mass. On 4th July 2012 at CERN, the European Center of the most advanced accelerator, the Higgs boson, was discovered using the Large Hadron Collider. You'll see more of it as you go by. So, in this talk, I'll present the theater and the history of that unique discovery. And by the way, I must congratulate Annapolis University to have a very forward-looking attitude towards collaboration. Please remember, science is just not India. Science is just not Calcutta. Science is just not from Taliban to Shambhazar. Science is for the whole world. And therefore, it's imperative for independent India in 2021 to have interaction with all our best friends and colleagues across the world. And I really mean that. That's my life's motto. You may not agree entirely. You know, everybody's saying about India is for India and so on. India cannot live within India. India has to live in this earth that you do know. But going back at the very beginning of beginning, the Homo sapiens' career in this planet, and the Homo sapiens learned to stand erect. And as he stand erect, and he looked at the sky and the various striking phenomenon like occurring there day by day, night by night, that struck him as most extraordinary. The sun, the moon, the fault of the sky, with numerous sparkling stars, bright and dim, must have appealed to him at the very dawn of his capacity to wonder at and indulges in certain amount of speculation about them. So those who are actually young, I'd like to appeal to them. The most attractive part and beautiful part of science is that to wonder at, like you wonder at a beautiful butterfly, you wonder at a beautiful flower, so you wonder at the striking phenomenon that is going on around you, but you have to look at it properly. If you indulge only through television and all this business, you forget about how to wonder. In Lower Egypt, the periodical overflowing of the Nile was noticed to have some connection with the heliacal rising of the sirens, and that eventually led to the idea of agriculture. Today, in 2021, it may not surprise you, but human beings took a very long time to understand the delicacy of how to have agriculture. They used to live as animals, kill other animals and eat them raw almost. But then agriculture started the beginning of the civilization that you do know. But I consider the father of modern science is Galileo Galilei, Italian physicist, mathematician, astronomer, philosophy who played a major role in the scientific revolution. In question of science, the authority of thousands is not worth the humble reasoning of a single individual. Galileo Galilei. This is the Leaning Tower of Pisa. If you go and see it, it leans and leaning, going on leaning, but it's still not broken down. And he did some fantastic experiments at that time with the cannonball and musket ball.
It's a facility. Optical fiber communication, physics, alter physics, some facilities.
Can you hear me properly? Hello?
Yes, sir, you are audible.
Okay. You're okay?
Dr. Somendranath Rai, please mute yourself.
So there he is showing Galileo, so-called Prince of Venice, how to use a telescope to look at the sky. In fact, Galileo is the first person who discovered how to make the telescope. First time in human history, they figured out that the solar system is not Earth-centric, but heliocentric. The discovery of heliocentrism. Helio means essentially the sun. Sun is at the center, not the Earth. Now, it may seem to be very simple today, but at that time it was certainly not simple to assert that. He almost went to jail to have said that by the Roman Vatican. And the great playwright Bertolt Brecht, he wrote a beautiful line, January 10, 1610, Galileo Galilei abolishes heaven, which means really from Earth-centric, it goes to heliocentric. Then comes Isaac Newton, 17th century. And Stephen Hawking, who was about my age in Cambridge, at that time he was not that ill, as you know, usually later on in his life. Hawking also took the chair in Cambridge called the Lucasian chair. And he once famously said, the previous owner of that chair was Isaac Newton, and he was not a very nice man. In fact, he was appallingly conceited fellow, but absolutely outstanding scientist. Émile Chaplet, a French mathematician and physicist who translated Newton's work into French and largely responsible for the spread of Newtonian ideas into Europe. Newton did so many things in his life, and of course the apple falling on his head led to the idea of gravitational discovery, is well known. My friend Jan Nallikar got a bit of a twig from that apple tree, and there he did an apple tree in Pune, discovering the laws of motion, gravity, calculus, refraction, rainbow, Newtonian mechanics, and Newtonian worldview. He's one of the greatest scientists the world has ever seen. Then in India, Maharaja Swai Jai Singh too, you know, this fine astronomical observatory were built in Delhi, Mathura, Benares, Ujjain, and Jaipur. Alas, we talk so much about poetry and play and history and etc., but there is nothing to talk about in terms of such temples of science as Jaipur. It's really fantastic. Jantar Mantar in Jaipur and Delhi and so on. I wish somebody has an idea to build that, but Bengalis are very inclined towards poetry and maybe a little bit of mathematics, but not certainly three-dimensional object like these things. The astrolabe is a way of measurement of the stars as you go and look at the sky. So discovered by the Jaipur astronomers. It was very advanced at that time. Then comes to Bengal Renaissance, Sir Jagadish Chandra Bose, 1858 to 1937, he discovered the millimeter wave. And the discovery of the power of millimeter waves as carrying a message from one part of the place to another, going through walls and so on, was a fantastic discovery. Unfortunately, Sir Jagadish missed out on the Nobel Prize, and Marconi got it because Sir Jagadish was not interested in terms of any kind of Nobel Prize or patent and so on. He was a bit of a rishi, actually. It's okay? Momita there is okay?
Yes, sir.
Thank you. This is the microwave instrument developed by J.C. Bose by some workers in Howrah, we believe or not. Today, everything is imported. That the kids don't learn how to use their hand. But J.C. Bose did that by workers from Howrah, our Howrah. And it's beautiful. I recommend the youngsters, all old stars, to go and see that instrument in an exhibition in Bose Institute. This is in the Royal Institution in London, 1897. He is showing the extraordinary marvel of millimeter waves going through the wall of Royal Institution. Then comes Charles Darwin, discovery of survival of the fittest and evolution. I wonder, this concept of the survival of the fittest, how applicable it is to human beings. You probably have noticed, although don't care too much now, human beings are the worst enemies of human beings. Human beings kill each other. Human beings have wars, one country to another. Human beings have killed the atmosphere, the climate. Human beings are terrible people. And no other animal species kill each other except human beings. Now, the awful thing about climate change is looking at us dauntingly. How long would the human beings allow the earth to continue the way it's continuing if we are not careful? Mass energy, everybody knows. This is Einstein's great discovery in 1905 and discovery of special theory of relativity in 1905, general theory of relativity in 1915, photoelectric equation at the same year, and then eventually with the OS and Bose-Einstein statistics. Einstein is serious thought in Princeton, as it were. Only thing common between Einstein and myself, I'm sorry to say, is that my desk at the office is same. Namely, mostly papers, you can hardly see me. That's only similarity, nothing else. Einstein, a musician, he was a first-rate musician, easily in a concert he can go by. Then comes Meghnad Saha, by whose name goes to Science Nuclear Physics, which I had the honor to direct, as was mentioned, for quite a number of years. And he changed astronomy to astrophysics, the quantitative measurement of so-called Earth matters and so on. And this first time it became measurable physics of the sky by discovering Saha ionization equation. And this is the famous equation, and as you can see, is non-trivial. It's not as simple as E equal to mc square, although probably E equal to mc square is far more profound. But this is no less profound than E equal to mc square. It's the high equation. It's in Bose. Jeetendra Bose was an Indian mathematician, physicist. He's best known for his work on quantum mechanics in the early 20s. And he wrote that famous paper correcting something which Planck has done. And that was rejected by proceedings of the Royal Society in London. So Jeetendra Bose had the audacity to send it to Einstein. And Einstein, although he was a very arrogant man, but he admitted this is a very important step in the right direction. And eventually it's called Bose-Einstein statistics. And from there, Bose-Einstein condensate, and the light particles, the photons, are called the bosons. So the whole bosons is full of the universe is full of light. So in some sense, the whole of the universe is full of bosons. What a wonderful thought. The Mahali Bacha has shown that the universe is full of bosons. This is the equation famous. For you, I translated that, not myself, by somebody else. In my opinion, Bose's derivation signify an important advance. The method used here gives the quantum theory of an ideal gas as a workout somewhere else, and this led to Bose-Einstein condensate. This is Einstein and Bose talking to each other. Einstein, as usual, Bhulovala Manush, which is very long pipe and smoking away. And Bose also, Bhulovala, used to know him as a boy, but somehow, because of his formidable respect for Einstein, he's wearing a tie, which is very unusual, in Bose. And he was an excellent performer as Raj, that Einstein was on violin. And today, I don't know what scientists do in terms of pastime. My interest, whatever it's worth, is not listening to necessarily Rabindra Sangeet, but listening to opera, whatever it's worth. So bosons. Another Indian discovery of Raman effect, which is used across the whole system of the so-called condensed matter physics or solid state physics. And he did that where? Here in Calcutta, with K.S. Krishnan, Indian Association for Cultivation of Science. I wonder when ISS people think and wonder about it. Because that standard of science discovery, that standard of research, is it there anymore? I have my doubts. He was the very first and so far the last Asian winning Nobel Prize. Sridhar was an interesting fellow. He actually got these ship tickets to Sweden before Nobel Prize was announced. Such was his confidence for him and his wife to go to Stockholm. He's the only person in the history of Nobel Prize. He did buy the ticket before Nobel Prize was announced. Now that looks that he didn't lack in any kind of confidence. This is another person, Homi Jehangir Bhabha, who was a product of Cambridge, England, cosmic rays, higher energy physics, and other frontiers of knowledge. More important, he is the father of the nuclear program of India. Bhabha Atomic Research Center, VECC, where I work, used to work and still work, is creation of Bhabha. He was a great man. He was a keen musician, and classical Western music was his passion. Nuclear program in India is doing not so well because the nuclear power projects getting derailed with agitation of politicians and so on and so forth. Fair enough, that's our democracy. Visionary behind three-stage nuclear power program. This is just a picture Deshpatrika had some time ago. You read it and make up your mind what it could be. Coming back to philosophy, the Indian concept was probably the most profound concept at the beginning of civilization. It's called Khiti Op Tej Murut Bom. Bom is emptiness, vacuum in our language, and that concept actually came to the mind of the people who wrote the Upanishad. And this is a very abstract concept. And if you know Khiti Op Tej Murut Bam, it's a Panchabhut also, interestingly enough. And this is our general concept that after a person's death, the soul gets diffused in Panchabhut. I guess it's not bhut or anything like that. It's the 5 species that I'm talking about. It's interesting to say. The Greek, on the other hand, stopped fire, water, and air, only 3. And they subtly missed the concept of emptiness or vacuum. Now today's world is such, you start from atom. Atom was discovered, the word, by Dalton at the end of 19th century. And it's still stuck, the word atom. Nucleus was discovered by Lord Rutherford, again in Cambridge, in the beginning of last century. 1932, neutrons were discovered and protons were already discovered by Rutherford. So the nucleus was discovered in 1932 in its full glory. To give you an idea about the size of the nucleus, if you have a football ground and compare the atomic nucleus to the football ground size, then a pea, mothershooting, in that football ground is equivalent to a nucleus. Then by 60s, neutron and proton was not so opaque. Scientists realized they're built with quarks and stuck with each other with gluons. The difference is they never come out from the little shell, the so-called billiard balls of neutrons and protons. They're permanently stuck within. And you should see in my story that as you go along, higher and higher energy, and the energy gets dispatched within a short volume, the neutrons and protons crack up, and inside the quarks and gluons show up on quark-gluon plasma. This is the four forces of nature. Isn't it extraordinary? Come to think of it. In the beginning, 13.8 billion years ago, 10 to the power 40 minus 43 seconds. Now, you see, I have debated with the best of scientists in the world. 10 to the power minus 43 seconds. What does it mean? Does it strike you anything you can conceive? I think not. You can use the word mathematically, arithmetically, but doesn't leave any impression. But the energy was awesome. This is just after Big Bang. 10 to the power 19 GeV. Within a microsecond, it's amazing in the universe, from 10 to the power 19 GeV, it has gone up to 1 GeV. And lots of things have happened. Electroweak broke, gut force broke, gut was the identification theory between strong and electromagnetic, and then weak interaction. And electroweak interaction was discovered by Salam, Glashow, and Weinberg, for which Abdul Salam got the Nobel Prize. So nuclear physics, the Cyclotron Center of Calcutta or Kolkata does do research on the nuclear physics. This is we built long time ago by hand, our hand. We didn't import anything. This was a test. And now I can say very proudly that our youngsters can build and unbuild the cyclotron very easily. Now, the youngsters must understand it's easy to import something, but you don't learn anything about the machine. So that if there's a crisis, you just have to depend on their whims and so on. They may come, they may not come. But now these youngsters are fantastic. They can cure any problem that this machine has. The big yellow thing is the magnet, and that magnet is as good as anywhere else, 200 tons plus, and that was built actually in Ranchi, that Soviet-India collaboration, Hatia, steel project. Then I decided to go to superconducting cyclotron. Superconducting cyclotron is testing a new kind of phenomenon experimentally, or so-called using a fantastic technology called superconductors. Superconductors means there is no resistance. So once you feed in some electricity, it will more or less go on forever and ever. This is remarkable, and you want to do that. It's very hard technologically. But I'm sorry, I have to say this, It's not appreciated very much in India. I remember there was a press conference they organized when the superconducting cyclotron started working. And there was a very senior journalist who asked me, so now, sir, we can do with the superconducting cyclotron the super detection of cyclone. I was so dumbfounded. I said, yes, you are absolutely right. Amazing, the simple knowledge of contemporary science is unknown to Bengali. So Bengali boys and girls are doing so well, but somehow it doesn't percolate down to ordinary person, which is by our fault, my fault. This is the superconducting cyclotron in full regalia. And you see how everything is smaller and it's working quite well now without much fanfare. We're carrying along the work very nicely because I don't want to have another embarrassment with journalists saying it's really superconducting cyclone now, right? Yeah. The cyclone is superconducting. That's fantastic. This is how complex it is technologically. And you see, it can be done here. This is the point. All these things we built ourselves. And this is not a laughing business. All the boys and girls I've taught in my life, which is a lot, they're always tending towards theoretical physics. I'm a theoretical physicist. But when I was given the job, I had to learn the technology. It's a great joy, I must say. This is again, very complicated magnet. And that was also built by the friends in Hatia, Ranchi. This probably would get bored in this thing, again the same thing. And at that time, Jyotibabu was a great patron of our system. Whenever I used to ask to come, he used to come. And he never said no to come to these functions. And this is laying the foundational stone of superconducting cyclotron. He was an extraordinary man, no question. He did not know anything about science. But somehow he did the homework and used to ask me personally, what is that, what is this, what is that, what is it? I was quite impressed by his personnel. And he was very impressed with the fact that we were doing such a thing. But there are not many people like him. I'm not talking about him in his politics, but his interest in science. This is the cyclotron center, present cyclotron room temperature. And I made a mistake of giving him a pen which has no ink. So he said in Bengali, and there is nobody there who understands Bengali except his Minister of Labor, who is dead now. Kali, Kali nahi. Very unfortunate. Poor chap was writing something in the notebook, and there was no ink in the pen because of my fault. I felt very bad. This is a great day for my life. August 25, 2009, when the superconducting cyclotron was the first internal beam. I'm trying to suppress my laughter. I don't know why. Stupid me. Everybody is laughing. It's great joy when such a thing happens in one's life. And these moments, by the way, don't come every day. It comes once in a while. And when it comes, you feel life has been worth living. K500, and there was an extraction was done shortly after that in December 2020. And then I'll bring to you another area, the medical cyclotron. This we had to buy because we had no time, and I was running out of time. And the medical cyclotron produces, this is how small but beautiful the machine, produces isotopes. And these isotopes are injected through a dye in your body, and they discovered the minutest tumors that you know in cancer, for example. And sometimes it is also treating cancer, for example, the prostate cancer. Thallium is used quite a lot for understanding myocardial infarction. Costs a lot. So now it is helping to reduce it. We have reduced the price to 1/3, I'm glad to say, and hopefully it will be cheaper for poor people to avail such a treatment. But the hospital guys are terrible. They want to charge the same amount of money. Anyway, so there's all, so I don't have time to go through this gallium also, soft tissue tumor, myocardial perfusion imaging of thallium chloride, etc., etc. Now we go to SAR, Geneva. You take your mind, off you go from Calcutta to Geneva. So from Big Bang versus Little Bang, you have Little Bang between two nuclei. And you have the task of building two huge detectors, very, very big detectors. Great challenge that was. And nobody believed us that we'd be able to build it. But my boys there looked very young at that time, all of us built it. And it was a huge object called photon multiplicity detector. You can see down there the size of the detector. Everything has to work properly. No way to say, I'm sorry that got tipped or that got this. They don't want to waste their time asking why. It was just out, straightforward. So this is the big PMD in 98 experiment, and that was done the first time in India, from India. So India made a great name for itself, large-scale collaboration. It was greatly successful. In the beginning, we had difficulty in terms of getting a footfall in SAL. Once we did, the sky is the limit. And this is actually a Brookhaven across the Atlantic, relativistic heavy ion collider. The circumference is 1 kilometer, and it's Kaviya. And this is a machine essentially to look at quark-gluon plasma. I don't want to go into boring detail. And a lot of Indians, institutions at my behest participated in that. And nobody would give us money to go there, because everybody who gives money, they have no idea. They think going abroad means having a great time, going to parties and things. But we had to work for 18 hours, 19 hours a day. This is the honeycomb detector assembly, a star experiment and LIC. And this is the famous Large Hadron Collider, 27 kilometers circumference, 27 kilometers one direction, 27 kilometers another direction. So 54 kilometers of very high vacuum machine. It's beautiful. We work in Alice, CMS, and Atlas. As Alice and CMS. This is the so-called muon arm detector. Done, the whole green object was done in Shah Institute of Nuclear Physics in collaboration with Aligarh, and it's beautifully done. And the chip you can see was designed in Shah Institute. You could do that, and that is inserted there without any failure, fortunately. And that time when you built it, I didn't allow any boys to go home. You see, for a Bengali boy or Bengali girl, going home is very bad, because they get spoiled and they eat too much, they sleep too much, and become slack. And they are no good. I mean, there's no discipline. And now with the things, I find that most of the time they're asleep. So if you're asleep, sleep is so much. When you find the energy to do anything, I don't know. Sleep and Bengalis and rice and mutton curry is such a dear thing to them. It's difficult to get them out of there. This is the Large Hadron Collider. Lake Geneva is there on the surface. Just imagine under the lake, there is a machine going on, smoothly working. It's a huge tunnel. You can get a feeling looking at that picture. And there's one magnet, another magnet, going round and round. Those who talk about technology should come and look at this machine. I want to assert to you that this machine was built not for technology, for discovering a Higgs boson, very fundamental discovery. But in the process, we discovered enormous amount of advanced technology which we never knew before. And this is how technology is discovered. Photoelectric equation was discovered by Einstein in order to prove quantum mechanics. But today, these damn stupid people going on taking technology. Why should I build something if there is nothing I can discover? Anyway, that's my philosophy. And at this age, I don't see any reason why I should change that philosophy. There has to be a driving force to comprehend and manage technology. And here, it seems either you look at the beginning of the universe, or you look at the Higgs boson, there is a reason for it. There must be. And just to get the technology as a sort of so-called pataka, flag, and have you marching with that flag of technology is, I think, is very short-sighted. Another picture, the proton moves 99.99991% of the speed of light, very close to the speed of light. And it goes 27 kilometers, 11,245 times a second. Now, how about that? Just think about that. In 1 second, it goes around so much to build up the energy. If that's not technology, I don't know what technology is. But we say technology and IT and all that business, frankly, is absolute nonsense. Why should I build a computer? We don't build a computer, by the way. India doesn't build a computer, all buy it and do some software for some company, and I'm great. I don't see any purpose of these things except earning a lot of money and kill your health. 8 o'clock to 10 o'clock at night. What is the point? I mean, there's other things to do in life, right? This other thing is very cold and very hot, both. When the two collide, the temperature goes up so much, it's telling you 5 times the heat and the temperature of the sun. And one temperature of the sun is 100 million Kelvin, MEK, sorry, Kelvin, and that tends to be 5 times, but very, very small place. And it's really a remarkable achievement by man, where you have such incredible temperature, incredible technology, probably the most advanced technology you can think of. By shouting about technology alone, you'll never be able to build such a thing. There has to be, again, I repeat, a driving force. This is the Higgs boson coming up. These are the various quark family, up, down, charm, strange, top, bottom, and Z boson, W bosons, weak interaction, electron-weak interaction, photons and gluons, and the leptons, electron, muons, and so on. This is the world at large that you know so far. Just collision between 2 protons and Higgs were discovered. That's the red line is the Higgs boson, 127 GeV. It's a beautiful experiment, I must say. This is the Alice. And on the left-hand side, the PMG is India. And the right-hand side, the green thing, the muon is India. Now, don't you feel proud? The bit of India built by Indian hands and Indian head is there in the largest accelerator of the world. Now, I feel, even at this age, very proud of it, actually. We built it from India, for India, INSA. This is myself and my good friend Hans Gudbrand in the belly of Alice. This is this huge quadrant being sent from Science Institute by plane to Geneva. And some blasted bureaucrat saying, you can't send it by plane, it's too expensive. I said, you don't know how much it means to us to build that thing. You can't count my money, my friend. Come and look at it. Okay, I'll come and look at it. After having looked at it, he didn't know how to get away and to approve the program. The bureaucrats can be funny. This is my work on Nyack, measuring the temperature of the photons when it's coming out. Same machine, same experiment. And so I think I'm talking so much, the time has come to be very nice to bring up Alice in Quackland, they call it. Alice in Wonderland. Louis Carroll. I read it out for you to amuse yourself. Maybe I stop there, I don't know. The time has come, the one has said, to talk of many things, of shoes and ships and sealing wax, of cabbages and kings, and why the sea is boiling hot, and whether pigs have wings. Lewis Carroll is saying to imagine the absurd This poem was written in one of my favorites. It is an atlas, huge detective, just a detective. And the middle is on fire, the DG, my friend, was. And this is the number of persons who work there. Hundreds and hundreds, thousands. But finally, they don't quarrel. See, there is a saying that 2 Bengalis is the limit. If there are 3 Bengalis, there will be quarrel. But they should go and learn how not to quarrel, but agree to disagree even, but not to quarrel. And this atlas is an extraordinary experiment of people from all over the world coming and doing some work there. Indian Sun is a great place. I recommend, rather than going to America, you go to LSC, you learn something. This is universe in the horizontal glass, I call it. You see, the glass is lying there, universe. You top it up, it becomes a glass. The Big Bang happened 13.8 billion years ago, and minus 10 to minus 12 second pp into minus 6 second lead LSC, and universe started working out. These are the various institutions that work in various labs and so on. But now there is a directive that we mustn't go out to do any work, to do everything in India. I don't think the Prime Minister means that way. We always overdo things about these so-called sayings, hospitals. This is the discovery, 4th July 2012 at CERN. I happen to be there in the audience, but not relevant at that time for me to be present. Rolf Fire is disclosing to the world that he discovered Higgs boson. Tremendous discovery. So for that little blip, if you can see, I have shown that by arrow, little blip, it costs a few $1 billion. Now, some people may ask, is it worth it? A few $1 billion to have this little blip? I said, more than worth it. Another experimental thing. Just look at this. Peter Higgs on the right-hand side, and the unpronounceable name, Francois Hinger. I think it's Belgium. Peter Higgs is said after getting Nobel Prize, oh, thank goodness, it's all over now. That's all he said. Little Bang has a Big Bang. I'll show you a picture and stuff. There is a Little Bang, and there's a Big Bang. Universe started with the Big Bang. This is the beginning, arrow of time. 1 million, 100 million, 1 billion, 12.4, 14, 13 billion. I've already said that time 10 to the minus 43 seconds. The temperature was huge. And universe was 10 to the minus 28 centimeters. Universe is expanding. Then comes electroweak epoch. Then comes the weak force separates from electroweak force. Walk to plasma. Disappears of antiquarks. Radiation of photons decoupled from matter and cosmic, and from formed cosmic background radiation. So curiously enough, nucleosynthesis you've heard about, I'm sure, hordes for 9 billion years. One doesn't know why, how. Supernova explosion, production of neutron star, a black hole, universe, and this is how it stands now. The universe is the most fantastic laboratory you can think of. But lastly, the visible matter is only 0.4%. And so-called dark matter and dark energy dominates. And the surprising thing, recently, means about 10 years ago, we have discovered the universe accelerating very fast because of dark energy. You don't know what it is all about. And there's dark matter and dark energy. And this is the idea of Brother Penrose, who can't come to my conference, but because of his age, he's 90 plus, just got a Nobel Prize. But he talks about cycles of time. So one yawn to another yawn to another yawn. And he is a colleague of Roger in Canada, Lee Smolin. He has a romantic view of the multiple universes that come in. Multiple means not more than one. One universe going to another one, and another one, and another one. And this is his view as a painter. So thousands of stars blink away forever in the backdrop, not around, he's alone and silent. Who is that? Rabindranath Tagore. At last. That's it. Thank you very much indeed. Any question? The question answer is on the agenda.
Thank you, sir. I'd like to request our host, Dr. Tamal Kumar Mukherjee, to please take up the questions. Tamal sir, are you here?
Yeah, I'm here, but
Yes, actually, I think at the end of the Professor Sinha's talk now, many questions in mind here in the participant. I think it's better you put the question in the chat box, and also we will address for Professor Sinha, say 1, 2, 3 questions, very acute question will place. So if please you have any question, you put the chat box, and our here organizer is here. We'll just selectively will also give this question to Professor Sinha.
okay, thank you, Professor Sinha, for your nice and illuminating talk. I think students have enough reasons why they should study physics, and there are much scope to contribute for the society at large. Now, we have one question from Rishabh Gupta. Sir, can you hear me? Professor Sinha, can you hear me? Okay, so this question is from Rishabh Gupta. So he's asking about neutrinos. As neutrinos are so weak interacting particles, so can they be used in research for the Big Bang and the Sun? And are there any applications of neutrinos?
Look, the trouble is that the voice is getting cracking all the time. So I suggest the following. You have my email, right?
Yeah.
So I need to collect the questions and send it to my email, and I will send back the answer immediately.
Sure. That would be best. Thank you. Thank you, sir. Thank you, sir. Yeah.
This is too much of a strain.
yeah, I can understand. And you are speaking over the 1 hour now. Yeah.
Sure.
So, Professor Sarkar, any concluding remarks?
Yes, actually, now come to the this end that yes, today respected Professor Sinha presented what not actually. He started from Galileo, Jagadish Chandra Bose, Satyen Bose, Einstein, Big Bang, and also a scope given to us to think how to transform Kolkata to Sun. And he did a long span, a time span from 10 to the minus 43 seconds to billion years, everything. And really, sir, we are very, very happy. And here the participants really got many informations that you have talked about, from the big thing to very small thing also. So, sir, will be very benefited obviously. And so I have one very just one sir, thinking in my mind, sir. How we is it possible how the tremendous energetic particle can control the bad nanoparticle in this crucial moment also? The tremendous energetic particle can control the bad nanoparticles So for example, today we are in this crucial moment. If we talk about this bad virus also. So is there possibility that energetic particle can control their activity and it will be helpful for mankind?
Yeah, again, it was not very clear, but it sounds interesting. Can you send the question to Saka by
Yes.
email?
Sure, sir. Yeah. But sir, your today talk is so enlightening us. And we are so benefited that you have talked everything in terms of time scale, in terms of space scale, everything, and give us a really motivating one direction also. Sir, we are very much grateful to you. Very happy, sir. Thank you very much.
Thank you.
Thank you so much, sir.
Okay, with this, we come to end of this session. So we are going to have a quick tea break for 5 minutes. So let's come back at 11:45, and then we'll have our next session. Okay. So please be with us, and please come back within 5 minutes. Okay. Thank you. Thank you very much.
And I'm saying one more student, Mr. Arnab Goswami, has posted a question. Arnab, as Professor Sina said, we will collect all the question and send him over email, and hopefully we'll get the answer very soon.
Kamal, this same link will work for the next session also?
I guess so.
Yeah.
Yes,
I guess so.
yes, sir. Yes, Tamal sir. Yes, ma'am.
Yeah.
The same link for all the invited sessions.
Okay, that's great.
So we are taking a 5 minutes break for tea and bio break. You may consider. So let's come back at 11:45. Thank you. Thank you very much.
Thank you. Thank you.
Hello, sir.
Please connect my PPT file. It is on. I have already started sharing.
Yes, sir. We can see. We can see your PPT. So
Yeah,
I'm
just putting the first slide. So just leave it like that, so that people come back from the tea earlier. I mean, because they were supposed to go to tea after my talk, I thought.
No, sir. In the program schedule, it is just for 5 minutes. Yeah, it is just for 5 minutes. Within 3 minutes, they are joining back.
Sure. Okay.
Okay. Thank you.
Hello, everyone. Am I audible?
Yes.
Yes, audible.
Yes, Dr.
Yes.
Mukherjee, you are on.
Okay. So let's wait for 5 more minutes and then we'll start. Sorry, 1 more minute. 1 more minute, then we'll start. So meanwhile, I request all the participants to be on mute, please. So our session chair, Professor Pandey is here, right? Ma'am, are you? Okay. Ma'am, should we start now or should we wait for 1 minute? Ma'am, you are on mute. Please unmute yourself.
We can start now, right, Momita?
Yes, ma'am, we can start. As per program schedule, now we should start.
Okay. So we are going to start our second session, or third session rather, after the tea break. So this session is going to be chaired by Professor Jeetendra. Professor Bhattacharya is a professor of physics in the Department of Physics of Habitable Zone University. Formerly, she was the professor and head of the Department of Physics, Jadavpur University. She has done BSc, MSc, and PhD from Jadavpur University. Her primary area of research interest is hadron structure phenomenology and exotic hadrons. Her research area also includes quantum plasma or the universe, fractals, and hypernuclei. She has published more than 78 publications in international journals of it. It's my pleasure to request Professor Bhattacharya to start this session. Ma'am, please.
Thank you, Toman, for your kind words. I'm audible.
Yes, ma'am. Yes, ma'am.
And it's a very good morning to all of you again on the behalf of Department of Physics, Adams University. I'm again welcome you to this national conference. So we are now starting our invited talk session. We are delighted and feel very privileged to have Professor Sandip Kumar Chakraborty, Director and Distinguished Professor, Indian Center for Space Physics, as our first invited speaker. Professor Chakraborty is a very well-known astrophysicist, not only in India. He is well-known all over the globe, and hardly he needs an introduction. Till some few words about him. Professor Chakraborty has done his PhD from University of Chicago, and he got honorary DSc degree from Gorbanga University. He was Stallman Faculty Fellow, Caltech, and he was in sabbatical at NASA Goddard Senior Research Fellow and Adjunct Faculty, International Center for Relativistic Astrophysics Network, Italy. So he has published more than 350 papers in the International Journal of Repute and have 830 research publication proceedings, books, etc. He has citation 11,840 according to the Google, and H index 53, and written a number of books, which is more than 10, and guided 45 PhD students, and 10 more is working under him. His area of expertise is astrophysics around black hole theory and observational aspect, the balloon-borne near space exploration, ionospheric science, and astrochemistry. Professor Chakraborty has tremendous organizational skill. He is founding secretary of Indian Center for Space Physics and in charge of this institute till its inception. And presently he is the director of this institute. According to the Stanford University survey, November 2020, he is the top Indian astrophysicist and 1.45% at the top of 1.45% of the whole world. And he visited about 50 countries all over the world. In the Indian context, he is in the top of the 10
Ma'am, you're facing a network issue, I think.
Thank you, sir, coming here, and I just request you to deliver your talk.
Okay, very good morning to all of you. I hope it is audible. I am a little bit distressed. Last 3-4 days, there is a virus going on in the and lots of cats are dying in my neighborhood. In fact, I have been running back and forth to the hospital, putting them on saline, etc. I really believe that these animals are far superior than ours. We are just very recent, 60,000 years only our history, but these animals are tens of crores of years ago they came, and some of them are hundreds of crores of years they have come. So the issue is that so when I talk about the origin of life, I really talk about the microscopic lives, and we are really the end product of it. And I will start from chemical evolution of the universe, and I will talk about it and since Big Bang, and I will talk about until today, how we were formed, this complex set of uh, molecules getting together to do some job. Now, this subject is really, as you can see from the title, it has a cosmology, it has mathematics, it has physics, it has chemistry, it has statistics and biology. So this is really a summary of all we know, supposed to be compacted in 1 hour. So when the universe started, as you know, that we were only a primordial fireball was there, but today there are galaxies, stars, planets, and above all, we ourselves are there with lots of animals and trees and whatnots. Now everything we see around therefore have to be made from scratch. They were not there 14 billion years ago when the universe started. So from 32 degree, 10 to the power 32 degree Kelvin at Big Bang, 13.7 billion years ago, average temperature of the universe has gone down to about 2.7 degree. Okay, radiation temperature, matter temperature is around 10 degree. And the rate of chemical reaction primarily depends on the density and the temperature. And therefore, all this, as the universe evolves, the chemical evolution is also taking place at a different rate, and also different types of chemical reactions are going on. So we will summarize the whole thing today. So from complex and from nothingness to get a complex species, really, if you think carefully, that we are formed after millions and millions years of events occurring at the right time, at the right rate. The probability of probability of probability of probability of probability and all to be ourselves today is so small, so tiny, so excruciatingly low, that we really are humbled that we exist at all. Okay, but this is possible because the laboratory is pretty big, and time we had about 14 billion years. So yes, we are made in this I don't know what is Zoom is bothering somewhere. Okay, so we are made in this large factory after zillions of trials and trial and error for a long time, and we are really the inevitable results of a set of very complex chain of reactions. Just as all the sentences of Shakespeare can be typed by a bundle of monkeys if they are given sufficient time and a sufficient number of typewriters. So they don't know that they have written Shakespeare, but they will do it because it is coming out of, if you want to wait sufficiently long time, you will get it. So how large is this factory and how long is long? And of course the universe is pretty big, pretty large. Today it is 10 to the power 28 centimeter big, and it was only a Planck length about 13.7 billion years ago. It happened about 13 billion years ago. I cannot say universe started because there was nothing before that. So, but it just happened. Okay, it's like Khuda. It just Swayambhu. Okay. So the issue is, they started after Planck era 10 to the power minus 43 seconds. After that, it got grand unification. 10 to the, up to 10 to the minus 10 seconds, electroweak forces were together. Then the particles were born. Okay, elementary particles. Then the nuclear reaction took place in the universe, and some of the elements were born. Then ultimately, after about 300,000 years, the radiations came out of left the matter, and them we call the cosmic microwave background today. After that, the atoms formed, then the molecules formed, the complex molecules formed, and then we are formed at the end. So if you see the scale, you will see that Homo erectus actually came 1.8 million years ago only, and Homo sapiens only 0.2 million years ago. And the first life started on Earth about 10 billion years ago, 10 billion years after Big Bang. That is on Earth. In other exoplanets, it could have started earlier, and that is possible. And in yet other planets, it can start later also. So on Earth, it is 4.6 billion years ago. The Earth started, and the life start is supposed to have started at 3.8 billion years ago. So this is the situation in a nutshell. Now, so we are at the end of a human chain, and if we divide the entire universe, the 13.7 billion years, into a 24-hour period in a day with 86,400 seconds per day, we are human beings are really the last 45 seconds just near midnight. Okay, so we are the end product, and the universe had a lot of other things to do. So we are not the universe, we are only a fraction of a percentage of something very humble thing. Now, when the universe started, it started with a primordial fireball and believed to be a quark-gluon plasma. And this plasma started cooling down, and the quark-gluon plasma ultimately started making these quarks started making our elementary particles before the universe was 10 to the power minus 10 seconds. Okay, and the neutrons and protons and other elementary particles were formed out of quarks, and they're all tied together due to the strong force. Now, but today we see this periodic table with n number of items and their isotopes, etc., huge number of them. So you have to make them out of these protons and neutrons. How to make them? Okay, so let us start the process. When the universe was merely less than 1 second, and these protons and the electrons, there's reversible reactions. They started becoming neutron and neutrino back and forth. The temperature was high, but as the temperature started going down, the neutron to proton ratio froze at 1:6. Why? Because neutrons are a little bit more massive, and therefore you cannot make any more neutron while you are still making protons. Okay, because neutrons require more energy to make them. Crudely speaking, okay, quantum mechanically you are doing it anyway, little bit, but that time the ratio was 1:6. This is a very profound thing, that the universe expanded in precisely such a way that the universe has 1 neutron for every 6 protons. So now these things is very dangerous also, because as you know that the neutrons started decaying, free neutrons start decaying at about 11 minutes or 10 minutes, some seconds, 615 seconds. So if you left to itself, if you don't trap these neutrons, they will all become protons. And if the universe was made up of protons only, boy, then there is no question of having life or even a planet or even I would say stars. Some loosely made stars, etc., could have been formed due to gravity, but then there is no neutron, so no element other than hydrogen. Okay, now so this is very serious. So universe cooled in such a way, without further reaction to trap neutrons within stable nuclei, the universe would have been pure hydrogen. No life would have been possible. So this is a probabilistically, as you can see, that the fact that we exist depended on how fast the universe expanded that time, so that it did not it had time to trap some neutrons. So how did it trap? It formed deuteriums. Okay, deuteron, the nuclei. Okay, so at t equal to 100 seconds, when the universe was only 100 seconds, 1.5 minutes, the deuteriums are formed, but the temperature was high enough, it is going back and forth, but at least some neutrons decayed, and therefore you had only 1 neutron per 7 proton. Earlier it was 1 neutron per 6 proton. Some neutrons got decayed and became proton. So we have now 1:7. Okay, but that's good. That is just enough to have produced today's universe, but it did not become 1:infinite or something. Okay, neutrons did not disappear totally. So the temperature was getting cooled down, so deuteriums could form for a while. Okay, for a while, because deuteriums did not survive. deuterium very quickly started trapping more neutrons, more protons, and started producing tritium and helium-4, helium-3, etc. So by 3 minutes, when the universe was merely 200 seconds, helium is formed, and in fact, after that, the helium nuclei is bound. Then the deuteron. So these reactions, once the helium-4 formed, it does not want to break down into deuterium anymore. Okay, and so reverse reaction was not allowed, and the universe already had the fate is frozen. Fate is frozen. Fate is sealed. This is what you must start the universe with. Take it or leave it. Okay, so deuterium is immediately used up by a faster process. This abundance is getting reduced since Big Bang. Very sad but true. On the other hand, because deuterium is very useful for atomic reactors, etc., or deuterated water, etc. But anyway, deuterium is very fragile, very difficult to keep them around. Now, eventually, temperature became so low that the electrostatic repulsion of the deuterium caused the reactions to stop. And the universe got frozen with 1:7 ratio. And if you now convert them, let's say suppose you have 1 neutron with 7 protons, so 2 neutrons with 14 protons. So then you add them up, you see 1 helium for every 12 hydrogen. So if you take in terms of the atomic weight, for 25 gram of helium, you must have 75 gram of hydrogen today. And if you look around the universe, lo and behold, almost everywhere you look at it, the universe has exactly this composition, the visible universe, that is the baryonic universe, roughly 23 grams of helium for 75 grams of proton and some other trace elements. So this directly proves that the universe started with Big Bang, because this is one of the biggest predictions of Big Bang, that you saw 1:3 ratio in gram wise. Okay, helium is to proton. Now the question comes, why the other things? What happened to the other things? Why Big Bang could not produce other things? Why it could not? Because very simple. Look at the periodic table. There is no stable element with atomic weight 5, and there is no stable element with atomic weight 8. So 2 heliums could have joined and become atomic weight 8, but it is unstable. Okay, then 1 helium could have joined with proton, made an atomic weight 5, but it is unstable. So there is a gap. Big Bang stopped any more nucleosynthesis. No more nothing, because nothing is getting stable, getting produced, and the chain is not propagating. The formation of elements is not propagating anymore. That's a sad thing, but true. Okay, good thing also, because as you know, that time is given, distribution was made so that the universe is not unduly clumpy in certain metal, and other metals are missing from the rest of the universe. So everything had a meaning, I think from today's perspective. So lack of stable nuclei with atomic weights 5 or 8 limited the Big Bang's dense and hot environment to produce only hydrogen, helium, and a little bit of lithium. Okay, little bit of deuterium trace elements. Now this is sad, as I said, but nothing can be done. So within 3 minutes, as you can see, this is the Big Bang nucleosynthesis. Started with proton and neutron. This is the proton and neutron, and they have been able to produce only hydrogen and helium and other trace elements. 3 neutrons, of course, decayed, and they have become protons since then. So future of the whole universe is frozen in just 3 minutes. The rest are details. Now, of course, these first stars started forming only at least after 700 million years ago. Million years after Big Bang, sorry, 700 to 1000 million years after Big Bang. There is nothing, no stars. Nobody has found any evidence that stars were present between the Big Bang and about 700 million years. James Webb Telescope is going to be launched next month, and we are supposed to see the first traces of elements. Okay, of the first stars, elements, traces of first stars which are born in Big Bang. So far, we did not see any first population 3. First set of first generation stars, which are called population 3 stars, made up of only early universe, at the early universe, made up of hydrogen and helium only. Okay, we see them in galaxies, but their age is much higher. Okay, so life was not possible earlier because there was no metal there, because there were no metal. Our stars were only first generation stars. Whenever they are produced, only hydrogen and helium. Hydrogen and helium cannot produce a planet, and therefore there was no life. Now, next step is, of course, to produce stars, and those stars, inside these stars, you have to produce all the other elements. Okay, George Gamow thought, he was the first person, 1940s, 1946. He said that the Big Bang will start the universe. Temperature would be about 20 degrees or 30 degrees. Sometimes he made it to 7 degrees. But ultimately, today we know that the cosmic macro background is 2.7 degrees. But he was the father of the subject, saying almost the right thing, almost 80 years ago. But these Big Bang, after the Big Bang, all the stars were born. Gamow thought all the nucleosynthesis could have taken place in, could have been formed in the Big Bang, but then ultimately Fowler, Babbage, and all they got Nobel Prize to show that no, all these stars actually formed this rich elements. So all the metals that you see are really coming from inside the stars, stellar nucleosynthesis. So a sufficiently hot star really will burn different elements in different layers. Our sun is not hot enough; it's only 10 to the power 7 degrees at the center, so it is burning only hydrogen into deuterium, and deuterium is forming into helium little by little. But helium cannot burn into carbon. Carbon cannot form muon, oxygen, silicon, etc. So in our sun, only hydrogen is burning. But there are massive stars where all these elements are being formed and then spewed out by supernova or through planetary nebula process, etc. Okay, beautiful. Universe has its own way of distributing. So the supernova 1980, for example, these are an example. You can see that how the stars, but these stars, particularly 1987, you can see that it burst and it just disappeared. It formed a neutron star at the center, and the matter is all spewed out all around. So these contain all the heavy elements that it produced for a few millions of years. Okay. We also see Crab Nebula if we have a small telescope, and at the center we also see a neutron star sitting there. Okay, Crab Pulsar. Now there is another star, as you can see, that Orion Nebula, this star Betelgeuse, is a ripe case for supernova. If you look at it, if you are lucky, it may become a supernova very soon, and the picture of Orion will look quite different. But now all these stars are making different stars at different temperatures, and they are burning different things. And faster they burn, faster their lifetime ends. Okay, and the slow and this, if a star is very light, it will just keep on burning slowly, and it will become billions of years old. Sun already has about 4.6 billion years old. It has already burned, and it has fuel for another 5 billion years. So we have not much to worry about from the sun's point of view. But of course, the earth may disappear because of other human nuisance that is going on, global warming, etc. So that is one of the reasons I love animals, because they did not really destroy the earth, and they kept the earth ready for us, and we have destroyed the earth. We are destroying the earth. Now, of course, there are nucleosynthesis around black holes also, but it's not a very important right now. A lot of things can happen around black holes, and those things can also be spewed out by jets. And so there are, after Big Bang, this is the best possible place where nucleosynthesis can take place. Of course, the stellar nucleosynthesis take place, but at a much slower rate. Now, so the universe really has mostly hydrogen. As I said, it's about if you take 100 gram of the universe, 75 gram is about hydrogen, about 23.7 or 80 gram is about helium, and the rest 1 gram, around 1 gram, is all the other trace elements: carbon, nitrogen, oxygen, etc. And as you know, that we are carbon based. If you are burnt, very beautiful set of carbon dusts form, and these carbons, these three elements, carbon, nitrogen, and oxygen, have the habit of making hydrides. Carbon's hydride is ammonia, methane. Nitrogen's hydride is ammonia, and oxygen's hydride is water. So these three hydrides are really, if you see in a planet, if you see around in the universe, and then you think that okay, there could be some chance to have life there. Okay, we'll come to that. And if we see the entire universe today, this is the variation. The hydrogen, if it is parts per million parts, you can see hydrogen is most of them, helium in terms of mass fraction, and the others are there, oxygen, etc., carbon. If you really see carefully, for every carbon we require, for every 12 gram of carbon, we require 32 grams of oxygen to produce carbon dioxide. So this oxygen, you can see that less than that ratio. That tells you that even after making that there will be some carbon left over, even after wasting using up all the hydrogen. So we have some chance to have carbon based life. If you go really below this, somehow it is cut silicon oxide. That is not the case. It is enough to make silicon oxide. We know that there are lots of sands in the beach, and all these are mostly silicon oxide. So silicon based life was not possible, although it's periodically in the periodic table. It has exactly same location, otherwise stability wise, and they also produce exactly the same kind of element that carbon molecules that carbons do. So second generation stars are necessary. Why? Because the first generation stars produce the cobalt, nickel, and all the metals, magnesium, nitrogen, and oxygen, and carbon, etc. And then they build the second generation stars. Okay, second generation stars have lots of metal, and not made up of hydrogen and helium alone. Lots of metal, like our sun. It is only 4.6 billion years ago when the first generation stars were born. Let us say almost like 13 billion years ago. Okay, or 12 billion years ago. So clearly, second generation stars are very useful to form life. Why? Because second generation stars we form from this matter, and then we will have all these elements, and therefore they can make planets, and therefore they will have lives. Okay, planets cannot be formed out of hydrogen and helium. Okay, they will not coagulate, they will not sit down together and form a hard object. Okay, and we have a temperature 300 Kelvin to keep RNA DNA going, nothing in doing. So if you want to have RNA DNA based let us say life, and not just purely hydrogen based, if it is there, of course, then it's a different matter, but it is not possible energetically. So to have lives, we must have the planets must have the complex elements, all the metals, and metals must have the second generation stars. So that's why it took some time for lives to form. Now, the universe had only so far light elements, and but the elements are not enough. You have to produce molecules. Okay, you have to produce molecules. The universe has started getting cool down, is getting cooled down, and it is not just sitting idle, and it is cooling down. Suppose it went down to 3000 degree Kelvin, and then all the electrons started recombine with the helium nuclei and protons, and they started making helium atoms, and the protons became hydrogen atoms. So this happened about 380,000 years after Big Bang. Okay, so all the electrons moving around freely and interacting with the photons in Compton scattering, doing Compton scattering, and beautifully producing blank spectrum there. Okay, optically thick, but they suddenly found that the electrons are missing. Why? Because electrons are now all trapped around protons and helium nuclei. So these photons, poor fellows, have nowhere to scatter anymore. They became free, and this is called decoupling, era of decoupling. They became free. They are now coming to our eyes directly from that era, and they are called microwave background. That time the temperature was 3000 degree Kelvin. Now their temperature has become roughly 3 degree Kelvin. So this must have taken place a redshift of about 1100 redshift. Very far, very farthest, very earliest things that happen. So these photons carry all the signatures of density fluctuations which were there present at the universe 380,000 years after Big Bang, and those density fluctuations are important because those were the fluctuations which produced galaxies in the very short run just after that. So it's very beautiful. There is nothing in thermodynamics that it says that everything is uniform. Universe was also not absolutely uniform that time. It had fluctuations. Somewhere density was higher, somewhere density was lower, and the higher density fellows produced galaxies, clusters of galaxies, and then the lower density fellows produced voids. Okay, and we see them all around. We see them all around, and so it makes sense. Everything is making sense. When the universe became cooler, all the nuclei forming respective atoms are neutralized, and of course ultimately they can reionize and produce. When the protostars are formed, the ultraviolets are emitted, and they can be reionized once more. Okay, so this is also the time just before the protostars are formed. This is also the time universe was cold enough around a protostar to form molecules, and the molecules, especially in pockets of cooler regions, you start forming molecules. Okay, so the next place for significant chemical reaction is is molecular cloud. Okay, so we had Big Bang nucleosynthesis, we have nuclear, we have stellar nucleosynthesis, but now all the periodic table is filled up. We now have to make molecules, and those molecules are formed in molecular cloud. So these are really the interstellar medium which are getting collapsing and producing star formation. So these are the star forming regions. These are the molecular clouds. Even in if a small telescope, if you have 4-inch to 10-inch, very good. Orion Nebula, if you can see near the dagger, you will see this beautiful Orion Nebula. This is a star forming region. You can see how many bright white stars, very bright, 40,000, 30,000 degree temperature, surface temperature, O-type stars are getting formed in this factory. Okay, and these stars have to be formed by Jeans instability due to collapse and fragmentation. Repeated collapse and fragmentation, you have to produce stars, and they take about 100,000 stars are produced at a time. Okay, so these are the typical molecular cloud, a small part of it, just to show you how big they are. Even a small part of it, even a small corner of it is much larger than the solar system. Okay, so these are the huge set of molecular clouds which have produced stars, and these are the clouds where you have to produce very complex molecules before you can start forming lives. Okay, so these stars are not just spherical stars. Everybody has angular momentum in this universe. Okay, either you have it around one origin, or if you have it around another origin, or angular momentum is origin dependent. Now, if it is radially falling to somebody, it is rotating around somebody else. Okay, suppose. So what is happening here is that all these so-called stars really are rotating also, so-called collapsing stars, and during rotation, centrifugal force is getting larger and larger on the equatorial plane, and centrifugal force is pushing the matter out, so they don't want to collapse in the equatorial plane. Equatorial plane, they produce a disk, and on the center, but the above and below along the axis, they collapse very easily because there is no centrifugal force along the z axis. So you end up producing a protostellar disk, and that disk is the nursery of all the planets. Okay, so one after another planets are born. We are no exception. Around the sun, we have already 8 planets. We had 9, lost one about 10 years ago, and because the naming nomenclature, Pluto is no longer a planet. But anyway, that doesn't matter at all. What it matters is that almost everybody has planets, whoever has metals in them, and big or small, few are in number. I will come to that. And all the star forming regions, if you see carefully with the best possible telescopes, you see zillions of lines, and there are most of them, unfortunately, not even identified. People don't even know who is emitting them. Okay, so there are infinite amount of things to discover out there. Okay, now this is, for example, the Orion KL region, hot core. Look at this. This is another hot core. This is IRS. This is another hot core. This is another infrared emitting hot core. So all these things are flooded with elements. So far, 250 molecules have been discovered in interstellar medium and circumstellar shell in our galaxy alone. And if you see other galaxy, extra galaxy, 69 have been already seen. Some of them are very complex, even C60, C70, 70 atoms coming together in the universe. Can you believe this? Because the density is very low. Density is only about 10,000 or even fewer than that. So how do they come together, so many of them? Because the universe is laboratory, is there for a long time, few billion years. Now, so look at this universe today. How can we produce these complex molecules? Molecule temperature is only 10 degree, frigid condition, 260 degree below zero in terms of degree centigrade. Particle number is only 10 to the power 4 particles per cc around. Compared to the density of this room that you are sitting in, 10 to the power 19 particles per cc. And the universe has only 10 to the power 4 particles per cc in this molecular cloud. So 10 to the power 15 minus 10 to the power minus 15 bar kind of thing. Very low, whatever that means. Even the best possible laboratory vacuum instruments are not being able to reproduce the universe's vacuum. Okay. Biggest problem is how to produce even the simplest molecules and even hydrogen molecule. Okay. The most important feature of this universe is that as soon as it started making some metals and it is cooling down, it started forming dusts. You hate dusts. All of us hate dust. Entire house is flooded with dust all the time. But these dusts, if they did not exist, there would not be even hydrogen molecules or other molecules. Why? Because dust bodies, okay, interstellar medium has about 1% dust. As you can see here, 90%, 99% gas. But this 1% dust surface is good enough. They're like catalysts. They bring the gases on them and meet. They just like Onughotok, catalyst or ghotok in a marriage. Two hydrogens come on the dust. They meet on the dust. They've decided to produce hydrogen molecule. If they were moving around one around the other, mean free path is so big, nobody will meet each other in their entire universe lifetime. Okay, almost. So the issue is dust help to produce the lighter molecules, H2, HCN, the poison, water, OH, and carbon monoxide. All the bad things were produced on the dust. Hydrogen cyanide, CNs. Okay, very easy to produce them on the dust. And of course, the massive things will be produced, but bigger complex molecules were produced after using them repeatedly. Of course, there are other catalysts. Clay, for example, is a good catalyst. So we trust in dust. Dust, if no life would be possible without dust as catalyst. And there are typically two types of dusts. One is olivine and the other is amorphous carbon. Okay. So when the carbon, oxygen, etc. comes out of the stars, there could be heavy. Their region could be rich with carbon, or the region could be rich with oxygen. If the region is rich with carbon, then all the oxygens are used up with carbon dioxide, and you can see that some carbons are left over, so that will be called amorphous carbon type dusts. If it is less carbon, then all the carbons are used up for carbon dioxide, and mostly oxygens and metals, magnesium, silicates, etc. will be produced. They will be called olivines. Okay, so mostly these two types of stars are there, dusts are there in the star forming region, and all the hydrogens, the hydrogen or oxygen, they jump on them, they hop around, they meet each other, say hello, and that process produces simple molecules. Then at some point of time, cosmic ray kick them out, or some jittery, there is a desorption energy. As soon as the dust becomes hot, they release these things to interstellar medium again. So there's a symbiotic relationship. They come and go, but these dusts remain. These dusts remain until and unless the star is about to form by ultraviolet. The dust actually melt away, and that's poor thing, but nothing can be done. Now, these contributions of grains and ice towards the understanding the chemistry. So these grains are there, dusts we call grains, and then on the top of them there could be hydrogen, water ice, and then there could be new molecules forming on ice also. So there are ice chemistry, there are grain chemistry, apart from gas phase chemistry. Gas phase chemistry is very weak because the gas itself, the number is very low, 10 to the power 4 per cubic centimeter. Even then, of course, most of the things are coming out from the gas phase. You can see the understanding of the problem, that the molecular hydrogen formation. We are writing paper on 2005 that how to produce molecular formation in a monthly notices. This is one of the high cited journals. So this says that the subject is really interesting. Not only interesting, we knew very little of the rates of how they are produced, etc. Main question remaining is, can complex molecules are produced, where biomolecules are produced by this process, and how life is originated. Now, first thing that a lot of people started in 1950s, started making molecules, very simple molecules, carbon monoxide, sulfide, carbon disulfide, and CN, etc. But I and my wife, Sonali Chakraborty, professor in Maharaja Mandir Chandra College, we decided that, okay, why not produce very complex molecule? Maybe the DNA, RNA constituents, adenine, guanine, cytosine, and many other amino acids, glycine, alanine. People did not think about it. I said, why not? Because people, they have to be produced, and they have to be produced by somehow. Okay. So, and unless they are produced, there is no life form. After life form, rate of equations may change. But there are other biochemical reactions, but you have to produce them anyway. So we made some assumptions, and we showed that yes, under some assumptions in the solar system, you can all the glycolic acid, lactic acid, adenine, glycine, alanine, all these things can be produced to a very large extent. Okay. Of course, our rate was very high. we chose a two-body reaction where and the grain chemistry was chosen at a approximate rate. But this is the starting point of a subject. People took it from there. And today this has become an industry. How to produce complex biomolecules? Can we observe them? Can we see glycine? Can we see precursors of the thing, etc.? So this is 2000. I would say that this is an interesting thing. This paper, as soon as it came out, John Buckle from Pisa University wrote me an email, God bless you. This is apparently really something that we did which without knowing that much that its implications. People got mad, all kinds of newspapers all around the world, and also the media also added some there too many Jews. We never said that but they added Anandamala. This is 2000, in the year 2000. All the newspapers around the world covered it. Why? Because this is the first time we are showing amino acids can be formed during star formation. Okay, this is very similar to George Gamo's thing. 1940s, they say that okay, everything started with Big Bang. He predicted temperature wrongly, but the factor of 3. But the idea was okay. He predicted cosmic micro backgrounds would exist, and it exists. So, and he also said that nucleosynthesis should form somewhere in the hot places, all the metals, and it formed. But not only Big Bang, but also stellar nucleosynthesis. So there were, since the rates were not known, we go a factor of few here and there. Even the chemical reactions, there are many pathways one can use. We use a particular Stecker synthesis, for example, to produce the amino acids, which are followed inside the rocks. The amino acids are formed. We see them meteorites, and in fact, they have been formed by Stecker synthesis. On the surface, they could be different method. So fundamental difference of you have to be very careful using equations, chemical reactions in the universe. Why? Because the chemical reactions before and after the self-replicating RNA molecule was formed are completely different. Why? Because before RNA is formed, you can use the laws of chemistry and physics, but after RNA is formed, you have the process of the natural selection. It has a different kind of chemistry, a biological chemistry, the temperature, and sometimes even the lower entropy system can form. For example, we as a living being, they actually low entropy. We would not be formed by second law of thermodynamics left to itself. Okay, so biologically decided reactions are different from the chemically decided reactions, and so even if our rates are here and there a little bit different, it does not matter. It is messed up by the biologically decided, dictated rates. For example, the methane you can produce by energetic purposes. For energetic purposes, you can produce in the laboratory and think about it how much to produce. But as soon as the metabolism starts in lives, methane is produced. Now, how do you get the rate of methane formation in after the metabolism started? So these two are different things, and so therefore it is. And also the third point I wanted to make is that this is highly non-equilibrium thermodynamics. Nothing is stable in temperature like in the laboratory. All the rates, reversible rates you use to get a rate equation, rates, and you get the rate coefficients, but these coefficients may not be valid in the interstellar space because they're non-equilibrium thermodynamics. Very important thing. So although we can say that yes, these will be formed, people should start looking for it and then get back then try to do back calculation to see what could have been going on. Universe is something we cannot produce in the laboratory just like that. It is done, it is there, and we have to just observe it and try to understand it. So many star forming regions already include the formation of complex molecules. All the stars, when they are born, when they're collapsing, you started forming these complex biomolecules. Take it or leave it. Now, whether they will form a life or not depend on whether the planets are formed, whether planets are in habitable region, whether the temperature is good enough to have a Goldilocks zone, so that whether the water can be stay in a gas phase or a water, liquid phase and a solid phase simultaneously, what is happening on Earth. So these are n number of other factors are there. So, but generically, all the star forming regions will be producing adenine, guanine, cytosine, and all these chemicals, which could have easily been formed life. So, so we are missing a lot of lives because there are some stars are not cooperating. Okay. Now, so some facts it is certain that many amino acids are formed in space. It is certain because we see them in Murchison meteorites. So far, amino acids have not been seen in direct observation, but it technologically very low. We also predicted very low. People have predicted even probably lower by a factor of 10 by different process. But that is not the point. People have been able to see the precursors of these amino acids. That is good enough. That means given technology, we will be able to. That is what Professor Vikas Sinha said. If technology should be improved to do some science. See glycine, if you can see them. See alanine. Even if they are very small amount, you already know, yes, some form of life is about to form out there. Okay. Technology must be driven by science. And this has been proven hundreds of times, like femtosecond technology. Ahmed Zoel, he drove Bell Laboratories to produce femtosecond instruments, okay, so that he can do science and get Nobel Prize. And the Murchison meteorite, for example, I wanted to show, there are 17 to 60 types of amino acids have been seen, varieties of. This is aliphatic hydrocarbon, aromatic hydrocarbons, fullerenes, carboxylic acid. All these things are seen in meteorites. How do they form there? These are frigid conditions, exactly the way I said, exactly the way we wrote in 2000, that they will be produced during star forming region, and some of them will produce planets. Planets will be destroyed, will destroy them because that's too hot. But these meteorites will smuggle them around. Will go out, like in wood cloud. We have plenty of meteorites sitting there, and time to time they come, they bring all these amino acids. So early solar system, it was very hostile, and all these meteorites were hitting the earth, and they brought ice, they brought water, they brought all these amino acids, all these oily substances, floating on the sea, and then they got together by complex process, churning by tides, sun and the moon, and it's a huge laboratory. The entire universe, entire Earth was flooded with water. Okay. Now you can see that the number of glycines, alanine, all of them are present in meteorite Murchison. Okay. So how did they get there? They must have been produced. The fact that you cannot see them in certain place because they are tenuous, your technology is not good enough. Now from complex life to complex molecules to life is a different thing. Now we have been on the Earth, we have seen that the complex, the earliest possible microfossils sitting there in Australian, Australian sea beach, stromatolites, etc. They're 3.7 billion years old. Monocellular life continued for about 1 billion years, and then monocellular life started about 3.7 billion years ago, almost like 1 billion years after the Earth was born. Okay, so most of the elements were already present on the Earth because they came from meteorites, and you just have to collect them together and allow them to make bigger and bigger on the sea surface, and at some point of time you produce RNA, DNA like molecules. These are accidents. As I said, the probability have to be calculated, but given large laboratory, it is nothing. You will produce sufficient amount. So in the Earth, life was originated, from during the, as I said, just to summarize in here, that the gas is getting when it is collapsing and producing the sun, it is producing already the biomolecules, and these biomolecules got into meteorites because they survived in meteorites, but not in the planets. Okay, if you consider Mercury, Venus, they're too hot even today. So even if the meteorites bring them there, it will evaporate, or it will destroy all those amino acids. Earth is a beautiful place. Earth is in a habitable zone. I have put it right here in the middle of picture. You can see that the Earth, our third planet, is in a habitable zone. Temperature is around 300 degree Kelvin, just enough to run to make these complex biomolecules into much more complex form, so that we can self-replicate. We can put a boundary around us with the oily substances, lipids, and we call themselves cells. So monocellular form, and this monocellular, they broke into pieces, hang around for in a different environment, and they become bicellular, and the more and more complex molecules are formed as we required them. Okay, and the Darwinism started because the beauty is that all these processes are not very sensitive to exact temperature and density. In different temperature and density on Earth, different places, equations, the reactions can still go on at a different rate in a different little bit of different final product. So we see this all the diversity of planet of the lives. Okay, so this small planet diversity is astounding. That is because these reactions did not obey the chemical rule of precise thing. There is a window, not narrow, where reactions can still happen and still produce diverse life form. In other stellar system, naturally, we are not preferred planet. We are not God's only creature. God does not love us at all. Okay, there is no reason to believe that. It is not for us only the universe started, though some people believe that. Issue is we are around a generic planet, in a generic planet around a generic star in a generic galaxy, and there are virtually infinite number of such galaxies, 10 to the power 12, and in every galaxy 10 to the power 12 stars, and there are some of them about 10 to the power 7 of them will have lives if I calculate properly. Okay, all you need is that it has to stay in a habitable zone. Okay, and then Frank Drake, in 1960s, he said, look, I know exactly how many planets will have lives. Just multiply all these fractions, but I don't know what the numbers of each fractions are. I can have an educated guess. So there is an average rate of star formation, fraction of good stars having planetary system, numbers of planets around these stars within an ecocell, and fractions of those planets where life can develop, fractions of life species that develop intelligence. So naturally, this is a very normal thing to write down, very difficult to actually quantify each of these fractions. But it is, even if you put very small number, conservative numbers, in our own galaxy, we can have about a crore, 100 lakh or 10 to the power 7 planets where lives can be around. Okay, so the life in the outer world is not unlikely at all. The other world should be there, as I said, that we are just generic planet in around a generic star. Of course, it helped. The star is a single star, it's not in a binary, so tidal forces on the planets are more stable, more predictable, and let us say the distance is such that the temperature is 300 degrees, and its orbit is in a circular orbit roughly, so that whatever you make in the summer does not get frozen in the winter, or whatever you make in winter does not get evaporated in the summer. So the circular orbit helps. And all these things help. The magnetic field helps from hostile cosmic particles, from solar particles, and whatnot. So it has right set of, let us say, environment to nurture us. All right. We have an atmosphere, and it is an atmosphere which protects us from ultraviolet. And so what else do we want to form life and hang around? Now, Kepler, for example, this planet, this satellite, discovered thousands of planets. 2,500 planets already have been discovered, or exoplanets, where life can almost form. This is an example of, let us say, 3 planets around a star in a star. This is another example. You can see that a star has been suppressed because it's too much light. You can see there are 4 planets rotating. They are real photographs, real images you can see. So it may you may get excited to see other worlds. Yes, there are planets, there could be lives there also. Look at this distance, only 20 astronomical units. So we are almost there, of course. But surprisingly, that is the makes us so unique, that all these planets which are discovered earlier, before Kepler, mostly all the big planets all the systems were discovered which are big planets like Jupiter, because they're part of the star and the star part of the planet, and their center of gravity is different, and therefore their orbital period, Doppler shift, you can always identify them and get the mass. But now then after the satellites went out, you see lots and lots of planets. Unfortunately, the Earth-like worlds is not there. Okay, 1 or 2 people say, okay, we can say it is Earth-like, but what do you mean by Earth-like? Orbital period is around, let us say, a couple of 100 to about 900 is 800 days, and its mass will be same as the Earth. There is nothing vacuum, nada. Okay, but of course that doesn't mean it is not there. It may be very difficult to observe them. People are doing science on exoplanet, even the exoplanet atmospheres have been discovered. So we are getting there. Would we be excited? I will not get excited, because I am not excited that because this is Earth cannot be a single place in the entire universe of 10 to the power, let us say 24 planets are there. Why should we be alone? Of course, many conditions have to be satisfied. I already mentioned masses of planets, etc. I don't have really time. Chemical criteria is there, protobiological criteria is there, evolutionary criteria is there, and so ultimately these things formed complex things. Let us say Earth was formed here. I summarized it. Earth was formed here. Then first cells were produced about 4 billion years ago, 3.8. Then first eukaryotes and the oxidation metabolism started around 3 billion years ago. So these are you can see the prints on fossil prints on oldest rocks. Okay, you don't have to guess it. It is there. Multicellular organisms are required when you wanted to do many things together. We call it manipulation. Mani means hand in Latin. When you really want to do a lot of things, by one hand you do one thing, other hand you do another thing. Your eyes, you are required to see something, while your legs maybe you are still walking around. You require a lot of organisms. Okay, and for organisms you require multiple cells, and therefore multicellular things are more advanced. Does not mean more intelligent, could be very stupid like us, but it is there. Evolution is inevitable. Okay, so summary: constituents of our universe is changing every moment. Life formation is inevitable in the vast laboratory where chemical evolution is taking place such a long time, even if the probability is very low. We are a generic planet around a generic star, so not much special. We are not special astronomically. It is likely that life is present everywhere in the universe. A conservative estimate suggests about 10 to the power 7 planets to have civilized life in our own galaxy, Milky Way. Thank you very much.
Thank you, sir, for your wonderful and illuminating talk.
Thank you.
You have made a beautiful journey for us from Big Bang to the creation of life. So is there any question? Dr. Mukherjee?
Yeah, there is one question from Showman Roy. So he wants to ask, I would love to hear from you about how the forces like gravitational force and other nuclear forces came into existence after Big Bang.
No, see, this is that is $1 billion question. The grand unification theory is there, but it has only combined only few forces, and even with the gravity, it has not been unified. Therefore, we don't have a real theory of quantum gravity. So the theory is not really complete yet, and I am not the most competent person to say that why the universe started, whether all these forces were together during when the universe just started. I am sure it was there, but so far we don't have any theory to show it. So I will go for the next question. This is really particle physics early universe question.
Okay, sir. We have another question from Jeetendra, who's our first year student. So he's saying that if space is expanding, then in such areas in universe far away from us, where it's already much expanded than the region nearby us, can the particles that make up the vacuum contribute through evolution? Equation, right?
Or somehow it is getting interrupted. I got basic idea of the question.
Yeah, yeah, it's a big question. So
no, I got the general idea that the question itself is not really correct. For example, just as we cannot say that the universe started and what was before the universe, this question is really not a real question, because the universe happened. Okay, now similarly, universe is expanding. It is not expanding into another space. Universe is creating this space on its own, and wherever it is expanding, it is becoming the universe. So basically, the stretching of the space-time, stretching of the manifold, or the space-time geometry itself, there is nothing beyond this manifold, so it is not getting expanded into some other universe. It is not like a bucket of water or something sitting there, and you are only a cup of it is the universe. Okay, universe is whatever you see with the velocity of light, it allows you to see, is the visible universe. Okay, and whatever you do not see, there is no causal connection with us. They will never influence us because nothing is moving faster than the velocity of light. So what we see is the universe, and we see them expanding, going away from each other. Everybody is going away from each other, just like if you take a balloon. Everybody knows that if you take a balloon and put a larger number of dots on them, and if you just make the balloon bigger and bigger, all the dots will go away from each other, and everybody will think that everybody else is going away from each other. Everybody will think that they are the center of the universe, and everybody is going away from them. That is not true. Every dot is the center of the universe. Similarly, from us, we see all the galaxies are going away from each other. But from another galaxy, if you go to Andromeda, you will also see others are going away from each other. So universe as a whole, this space-time is stretched in such a way, everybody is going away from each other. So it is not going away from you to somewhere else. Okay, it is really the space-time. It is you take a scale, of 12-inch scale, you put 12 ants on each inch. Okay, one ant on inch number one, another ant on each number 2, etc. And you stretch the scale. All the ants will still be away from each other by 1 inch because they are sitting at 1, 2, 3, 4. The numbers are not changing, but the distance between them is changing. Okay, universe is like that. We have a scale. The scale is getting stretched by the primordial force. Now we really don't have exact theory yet why universe started at all or happened at all, really.
Okay. Thank you, sir. There are a couple of questions, but we are running out of time.
Yeah.
So should we take another question, or should we move on to the next speaker?
Taman, you just take one question, only one question.
Okay. So the next question is from Rishabh Gupta. So he's asking, sir, how accurate image of our universe can we get from James Webb Telescope?
Very good question. James Webb, the telescope project scientist John Mathar, has just sent me an interview yesterday. He is the PI of this telescope. In fact, you will read all about it in my Telegraph article on Know-How, 13th of December. My interview with the James Webb principal scientist. Okay, John Mathar, who got Nobel Prize for discovering cosmic micro background in 2005. He will get again. But very simply put, the James Webb will find out the first stars, formation of the first stars in the earliest universe after decoupling. Okay, so that is our hope. That is one of the first things that we want to know. Let us stop it there because it has enormous scope. Please wait for that article in Know-How. You will get everything there.
Okay.
Thank you, sir.
Thank you, sir. Thank you, sir, for answering the questions. And ma'am,
when it is come the question of universe and life, the question is never ending, but we have shortage of time, so we have to end. Thank you, Professor Chakraborty, for your kind accepting our invitation and giving us this talk. In spite of your very, very busy schedule, you have made time for us. We are really looking forward to see you at our campus somewhere in future. So thank you so much. Thank you so much, sir.
Thank you very much.
So we start the second.
Yes, ma'am. We start the second.
Yeah. So the second invited speaker of this session is another very well-known condensed matter physicist, Professor Saurabh Basu. He's a professor of physics at IIT Guwahati. He has done PhD from IIT Kanpur and have postdoc at TIFR and Queen's University, Canada. He was visiting faculty at University of Frankfurt, UKM, Kuala Lumpur, Bilken University, Turkey, visiting fellow ICP Trieste, Italy, and he has more than 122 publications to his credit, and main area of research interest is theoretical condensed matter physics, quantum information, topological material, anomalous Hall effect, correlated electron system, topological insulator and alta core system, and many more. Today he is going to talk us about vanishing of topological invariance in a semi-direct nanoribbon. Thank you, sir, for joining, and I just invite you to deliver your talk right now.
Yeah, thank you very much, Professor Bhattacharya. Then also thanks due to Professor Sarkar, who had actually contacted me many months back, and I was quite happy that this conference is coming up very nicely. And let me share my things. Are you able to see the screen?
Yes.
Okay.
Yes.
All right.
Yes.
So maybe I'll just stop the video and start with the presentation. Once again, it's a privilege for me to be talking here. And I had the good fortune of listening to last few minutes of Professor Chakraborty's talk earlier. And it's quite illuminating. Probably, things about the universe and other things about stars and so on are much more fascinating to students. But here I'm going to talk about materials and condensed matter physics and topological insulators and so on. I hope that they are interesting as well to the audience. So the topic, as has been told, is that it's topological invariance and the vanishing of it in semi-Dirac nanoribbon. And we'll have to understand what's a Dirac nanoribbon and then so on and so forth. This has been done, the work has been done by my graduate student, Shayan Mandal. And so let's start with this and see that what we can offer to the understanding of this ongoing research on topological materials, particularly graphene and so on. So the objective is twofold. One is to talk about these topological invariants and how they vanish in two kinds of topological insulators, one without time reversal symmetry and one with time reversal symmetry. I'll explain each one of those, the words as they come along in different parts of my lecture, and hope at the end you'll get a feeling that what we are trying to do. So the topological insulators may not be clear, at least to the students who are not working in the field. So let me give you an example of topological insulators. You see the left cone, which is here, it's just that two cones that touch at a point, and if you somehow build up a gap at the touching point, then it looks like this, the one on the right, but then it becomes an insulator, a normal insulator that we all are familiar with. But if there are some edge states which carry current or information, or for that matter, a particle can travel along that green line, and then it's called as a topological insulator. And their states, if you actually try to visualize it in a real space, then in a three-dimensional sense, you'll have states which carry current are at the surfaces, and the bulk is insulating, or in two dimension, where you have currents that go around, along the edges, but the bulk of the material, which is inside the material, it's insulating. So that's why they're called topological insulators. They're not insulating just like our normal insulators, which we are very familiar with from our early school days maybe. But these are materials which have generated a lot of attention and introspection about them, about their properties and their conducting properties. So if you say conducting properties of insulators, it'll evoke probably laughter that what we are talking about, because the insulators do not conduct, but these ones do. And that's what the main topic is all about. So, and then, as I said, that I'll talk about each one of the words. So I said topological invariant. Now, you see there's a cup on the right, which is continuously being deformed from being a cup to a donut. And if you are slightly unable to follow that, what's happening, then you see the picture on the left where there's a cup again, which is the slowly where the liquid rests is coming up. And eventually, where you hold the cup, that hole remains and it becomes a donut. So what I mean is that this mug and the donut, they belong to the same topology class, which means that the mug or the cup can be actually deformed smoothly without doing anything violent and get it into the form of a donut. So these are topologically similar, or they belong to the same class of topology. And this is what has attracted attention of the condensed matter people for all the reasons that you can even think of. That why should this, mug converting into a donut be interesting to condensed matter physics, and what is its relation to graphene at the end of it, and what are the relationships with time reversal symmetry breaking, etc. Those things are really interesting. And let's see how we can get into the scales inside of this so-called onion and get to the core part of it. So the topological invariance, it just looks like you see some geometrical figures on the right, which are of different shapes and so on. And the one that's on the left of this is called as it has some radii of curvature at the equator. The cylinder has something else, and the sphere has something else, and so on and so forth. So these curvatures can be quantified as 1 by R1 into R2. And this is called as a Gaussian curvature. And what we can do is that if we take closed surfaces, then we can integrate this Gaussian curvature. And it doesn't matter that whether you're talking about the left figure, which is some object like a drum, used for various purpose, and or the sphere. If you do that, it gives you a constant, and this constant contains a factor which is called as G, which has a name called genus, and genus means is the number of holes that are present. And one such example we have shown in that mug to donut transformation, where there is just one hole which remains intact as you smoothly deform from one geometric figure to another. And this has a name called as a Gauss-Bonnet theorem. This theorem has a name. So you may not be able to integrate this Gaussian curvature for all closed surfaces, but doesn't matter if there is a theorem that tells you that this is what is finally going to happen, then there are, job is served. So, so these are the topological invariants in actual topology, which mathematics people do. And so G is equal to 0 for a sphere because it doesn't have any hole, and G equal to 1 for a torus. So you can integrate this quantity, which is the Gaussian curvature, over this, the closed surface, and you can get this thing. We sort of try to connect to condensed matter physics, and this is Michael Berry. And it's just on a lighter note that we show his face, but his face is not important for us. What is important is a phase. So we want to know the Berry phase, if at all it exists for a given system. And I don't have time to really go through what is Berry phase, but that's in condensed quantum mechanics, that if the Hamiltonian is actually a function of certain parameters, and this parameters, if you change adiabatically and make those parameters come back to the same point where you started with by taking a 2π revolution, the wave function of the system may actually pick up a phase which is irreducible. It's not scalable. You cannot absorb it into the definition of something. So that's called as a Berry phase, pretty much like the Aronoff bomb phase in a different context. So there are different things called as a Berry connection, Berry phase, Berry curvature. And what we have or will be talking about is a quantity called as a Chern number, which can be obtained from what's called as a Gauss-Bonnet theorem, which I just showed you. All right. It's not difficult to get these quantities, and you just need to solve a Hamiltonian and get the eigenfunctions, which are called the block wave functions. Because these, suppose you can write down a Hamiltonian in K-space with proper proper translational symmetry, then you can get this UNKs, and then you can get the psi NKs and so on, which are wave functions, a well-known problem in quantum mechanics. And then you get a Berry connection by finding out the expectation value of this delta K operator, which is something similar to a velocity operator. There's also a minus I outside. So if you remember, the velocity is like minus IH cross DDK or del K. And in three-dimensional sense, it can be written as a gradient operator. These Berry connection, which can be talked about as a Berry vector potential, has a gauge, it has a gauge symmetry. And you can fix a gauge. So it is always possible that you make it undefined with the scalar chi, such that this A can be changed to A plus grad chi, and so on and so forth. And from there, if you know how to calculate the Berry connection, you can also calculate the Berry curvature. And the Berry curvature can be integrated over the entire Brillouin zone to get a Chern number. And that's how we said that there is something that needs to be integrated over the surface, which was a Gaussian curvature. So Gaussian curvature integrated over the surface, just going 2 slides before, the last line, it's exactly same as the line that's written here as well, which is which is called as C and called as a Chern number. So the Berry curvature is analogous to the Gaussian curvature. The Chern number is analogous to that 2π into 2 minus g, which I written. It's called as a Euler Poincare characteristics. And so there's a one-to-one correspondence between topology and condensed matter physics. And that's what made things so interesting and made us understand material properties much better. So, so basically, just like the Gauss-Bonnet theorem, we write down the Chern number. I mean, here it's written with n. So you sum over the filled bands and sum over. So what's the surface of the closed object? Here, the integration is over a Brillouin zone. So when you know how to solve a Hamiltonian in the K space, you know how to get the block functions. You also know the Brillouin zone. And when you know the Brillouin zone, you can integrate over the Brillouin zone in order to get what are called as, so this is exactly the analogous expression. And this was, told immediately afterwards. This quantum Hall effect was discovered in 1980 by 4 people called as, they're called as TKNN. There are 4 people: T for Thouless, K for Komoto, N for Nightingale, and the other N for Den Nice. And there was a PRL paper which was extremely nice and very compact paper written there, where they actually figured out that the Hall conductivity, which von Klitzing did that experiment, which is almost about 100 years later, the classical Hall effect was discovered by Edwin Hall, and he figured out that this. Say it again.
लैपटॉप है मेरा, काम नहीं करता अच्छा से। हम तो सेकंड हैंड 6,500 में लिए ही थे।
মোহাম্মদ শানাউল্লাহ আলম, প্লিজ।
भाई मेरा कितना खर्चा हो रहा है अभी?
Please mute your audio.
Okay.
Everybody.
All right. Yeah. So this was, this main finding of this TKNN, which said that the Hall conductivity is simply the Chern number and multiplied by a constant, which has the unit of conductivity. And so there's a very nice connection between the topology as one learns in mathematics and condensed matter physics. So this is what we had talked about earlier, that this is the Hall resistivity or the resistance. When it's swept as a function of the magnetic field, it shows these plateaus. And these plateaus are these numbers that you see are just the numbers that you see here, n. This n is the same as this n. And then you get different n's, and these n's are just quantized. And these are the topological invariants. Just to remind you that we have shown you one topological invariant, which is a transformation from a mug to a donut. Okay, so these are the nice plots of the Hall resistance, and the quantization of these Hall plateaus, as I said earlier, is a topological invariant in condensed matter physics. All right, so this is how things have started. People have started understanding that there's something much more fundamental in these in this particular experiment. And this was the first topological phase of matter, because the bulk was actually insulating, and the current, the Hall current, or even the longitudinal current, was actually carried at the edges of the sample. And because the bulk behaves differently than the edges, and that's why it gained the name as topological insulator. It's insulating in the bulk, not at the edges. So let me come to a very interesting thing about graphene. And it says that graphene was invented much earlier than it was discovered. And there's a picture of somebody called P.R. Wallace, who was appointed as a postdoc right after the Second World War by the Royal Military College of Canada. So this is where he first started his job. And there are a lot of talk about how to make green energy, especially the world was battered with the bomb on Hiroshima and Nagasaki, and people thought how to actually make energies which are more less destructive to human and better for the environment as well, and which is what we are talking about even now. So he was given this job of finding out the band theory of the electronic dispersion of graphene. And he tried a lot and he couldn't get it. And it took about probably 11 or 12 years before we actually arrived at the band structure of graphene. But since then, a number of people have taken it out of the closet, that is graphene taken it out of the closet. It was not discovered. So it was simply the passion for these theoreticians. All of them are very well known. The first, it was by Semenov. I didn't get a picture of him, where he talked about certain anomalies that are there in high energy physics. And he said that a condensed matter would be a testing ground for such anomalies and so on. And then it was the masterpiece of Holden, who understood that this graphene would be very interesting to study, where he put his real genius and said that you can get Landau levels, you can get Hall effect, quantum Hall effect, I'm sorry, without Landau levels. So the quantum Hall effect is intricately connected to the presence of Landau levels, but he said that there's no need of Landau levels. So you'll still have Hall conductivity and so on. And that started, shaping up a lot of research later on. And these three people that you see below, Thouless on the left, and Kosteles and Holden again got a Nobel Prize for this in topology and topological phase transition in condensed matter physics in 2016. So graphene has been finally, 2007 by these two gentlemen there in UK. They're called Andrei Geim and Novoselov. So they discovered graphene, and when they discovered it, they got a Nobel Prize in 2010. And a lot of properties that were sort of written down, and all these properties were very different than all the materials that were known even now. Very large carrier mobility, very large thermal conductivity, transparency is about really good. And it just looks like, the sheet that you use for packing children's tiffin. So it's that kind of a sheet. So it can expand very to a large extent. Then there's a very large Young's modulus. In fact, the Young's modulus and the very large tensile strength caused a lot of attention. But what is very important for us is the last one, which is the band gap zero. So it's neither a metal nor an insulator nor a semiconductor. And so people started wondering what it is. And so this is what it looks like with carbon atoms taking places in both the red and the blue dots. And when one calculates writing a tight binding Hamiltonian, that is a non-interacting Hamiltonian, one gets an electronic dispersion exactly like this, where there are 6 points in the Brillouin zone where it is, the band gap is 0. So these are conduction and valence band, because you're doing a diatomic lattice A and B, so you get 2 bands. The upper one is called as a conduction band and the lower one is called as a valence band. And if you zoom into one of those, then it looks like the low energy part of that looks like a cone that's inverted and touching against each other, pretty much something that we have shown earlier. So that's a Dirac cone, and something that immediately caught attention, that why should there be a Dirac dispersion, because Dirac is very specific to relativistic physics, and we know condensed matter physics is because of the the electrons and phonons, which are, none of them are relativistic objects. Okay, but here it's only the dispersion is relativistic. The electrons still move with Fermi velocity, which is typically 3 to 4 orders of magnitude, 3 orders of magnitude lower than the the velocity that you have for photons, which is light velocity. Once when something is understood, then people want to get to the next level and try to understand something more. And then they tried discovering materials just like graphene, other materials made up of, when you replace carbon by something else, such as silicon, germanium, etc. And then they found that these materials are slightly deformed as compared to graphene. Okay, so they have sort of, it's either deformed in the lateral direction, or they're deformed in the transverse direction, and you can make ribbons out of it. Ribbon geometry is essentially geometry that is infinite in one dimension. and it's finite in the other dimension, other transverse dimension. So this silicene is one example where things are, it's not exactly like Dirac, which is what we had shown, but it's like semi-Dirac. I'll tell you what semi-Dirac is. So silicene, germanium, and deformed graphene, or even, the material scientists have discovered graphene, and there are different kinds of graphene called as alpha graphene, beta graphene, or 6,6,12 graphene, and so on and so forth. Okay, so there are experimental realizations of these semi-Dirac dispersion, and our objective is to actually go from Dirac to semi-Dirac and see that what happens to the topology of that material, or topological properties of that material. So let us talk about the symmetries that is there in every field of physics, and they are called as parity, which is inversion, special inversion. And then there's a particle hole or particle antiparticle conjugation. So I'm talking in the language of particle physics at the moment. And then this time inversion, what we call as time reversal, and so on. And these things have, similar symmetries are there in condensed matter physics. So let's see what they are. So in CMP, condensed matter physics, you have, when you break the parity symmetry from graphene, you tend to go to what is called as the hexagonal boron nitride, where the carbon atoms are replaced by boron and nitrogen, and they definitely break what is called as the parity, or the spatial symmetry. And what happens to particle hole symmetry? Particle hole symmetry can be broken in a tight binding description when a second neighbor hopping is introduced. Okay, and most importantly for us, the time inversion or the time reversal symmetry can be broken by the magnetic field. And the student needs to understand that what is meant by a time inversion or time reversal. You don't actually make time go in the reverse direction, but make the person who's cycling there to go in the reverse direction. So the velocity is reversed and not actually the time, but in effect, we say t going to minus t. But what we want to see is that what happens when the velocity of the object or the particle or the person is reversed. So this is just a pictorial demonstration of this time reversal symmetry in magnetism. So you see a magnetic moment, which is written as mu, and which you can very easily prepare by taking a circular current. So a circular current will give rise to a magnetic moment, which is current into the area. If you apply the time reversal operator, the current will start moving in the opposite direction. Okay, so suppose you do that, that is, you change the direction of the current by changing polarities or whatever, then the magnetic moment also gets reversed. It's in the picture that is shown here. So it's slightly more complicated with spinor systems, where it is not only complex conjugation, but you have to also do a spin rotation. The sigma y is actually the Pauli matrix in the y direction. So what happens to a ferromagnet? If you do a time reversal operation on a ferromagnet, it'll still remain a ferromagnet with all the magnetic moments reversed. So this is what is known as the time reversal symmetry. So let's look at topological insulators with broken time reversal symmetry, which is known as the Holden model, which is what I said about Holden's genius of, without requiring a magnetic field, he broke the time reversal invariance. So he broke that, and he claimed that there'll be Hall effect, but there'll be no Landau levels, because Landau levels are very specific to magnetic field. Okay, so he said that take graphene, and just once again, I want to remind you that it's again an invention and not a discovery. Graphene was never there, but it's there. It's always there in the mind of these, great theoreticians. and so on. So you see a graphene lattice when where this red and blue, they denote carbon atoms. Now, what he said is that you introduce complex second neighbor hopping in such a manner that if you traverse in the clockwise sense, that is what I mean by clockwise is that, this red to this red is a clockwise hopping from this red to this red and so on. But if it is from this blue to the blue, it is actually anti-clock hopping. So he said that the clockwise hopping would be for the red atoms and anti-clock hopping for the blue atoms. And this way, he said there's a chiral hopping. So it's a direction dependent hopping. And also he included that let there be an asymmetry in the chemical potential at the right, at the red atoms and the blue atoms and so on. And it's easy to show that this system has broken time reversal symmetry. But what is not clear is that whether this will give rise to a topological insulator. And it turns out that it does. And when it does, then it generates a phase diagram where the Chern number, as I said earlier, that the Chern number is a nice indicator, it's a topological invariant. So if there is a space in a phase space or phase diagram which shows non-zero Chern number, it's a topological phase, and when it's a zero Chern number, that's a trivial phase. So the C1 equal to 0, as you see there, corresponds to normal insulators that we have all learned from our school days, and the +1 and the -1 correspond to topological insulators, which is what people are now talking about. Okay, so there's a distinction between the topological invariant being 0. So if I want to remind you that C1 equal to 0 is a phase like an orange or a ball or a sphere, okay, which has no genus. The genus is 0. These blue and the pink, these regions are like the donut, which has a hole. Okay, so we want to ask a question that what happens to such a scenario under the deformation of band structure? So can the tuning of the nearest neighbor hopping, will it help? Whether can we induce a topological phase transition, that is go from one phase that is a non-trivial phase to a trivial phase. So can we go from a topological insulator to a band insulator without breaking any of the fundamental symmetries that we have just talked about? Okay, and we'll simply deform the band. And if we do that, so this is called as a semi-Dirac, as I told you that there are some experimental realizations of that. So if you look at this, then this honeycomb has one T1 and the other two as T. So you break the C3 symmetry, which is not one of the C3 is rotation by 2 pi by 3, which is not one of those very essential symmetries of graphene for topology. Okay, and if you do that, so one of the hopping among the three is different than the other two, and you continuously tune T1 from T to some value, say 2T, then the dispersion is what is presented on the right, and you may not see it very well, but this dispersion is called a semi-Dirac, which is Dirac-like in one direction, say kx direction, and it's like a parabolic in the other direction. So in the ky direction, it goes like k square, and in the kx direction, it goes like k. Okay, so linear in k, which is like Dirac. So Dirac is like for photons, where you have energy equal to, say, hck, okay, or h cross ck, whatever. So this is the interesting part, that if we go from T1 equal to T to T1 equal to 2T, that is, we go from from Dirac to semi-Dirac, what happens to this topological phase? What happens to the Hall effect? What happens to all these topological invariants? And which is what I show here. So these are some band structures. So what you need to look at is the first one here, the one on the right, and the one that's last one, which is again on the right. You see both have gaps in the band structure. Okay, the electronic band structure has gap, but one is topological gap, the first one, and the one that's on the last plot is a trivial gap, and this is what we are going to show there. So this is the interesting thing that happens, and the system actually undergoes a gap closing transition, and the gap closing transition happens at these point where T1 by T is equal to 2, which means T1 equal to 2T. So the interest lies that in the fact that we are able to tune a transition from a normal band insulator to a topological insulator, or the other way that we are talking about here. So when you take a nano ribbon and try to calculate the what called as the edge modes, as I said that the topological insulator would have edge modes and trivial insulators do not have edge modes. So if you look at the first left figure, you see that there are two edge modes crossing at the points U and V, and this is truly the topological insulator in the Halden model. So if you solve Halden model for a nano ribbon, it gives you a band structure like this. So you have these dark blue regions are the bulk ones. So the top one is a bulk, the conduction band, and the bottom one is a bulk valence band. And there are edge modes that are crossing the Fermi energy. And if you go to the last one, which is a trivial insulator, you see that it crosses at 4 points, and they cancel. The currents would cancel pairwise, and that's what is shown in the yellow panel below. So you have a mode that is traveling on the right at the point U, or at the point V, it's traveling in the right, and at the point U, it's traveling towards the left, which we obtain by calculating the velocity. Velocity is the derivative of the band structure. All right. So this is what is written there, and so on. So now go back to those topological quantities that we have talked about. Let's talk about Berry curvature for this Halden model. So we calculated the Berry curvature, and for the Dirac case, you have these, you get these nice lines which you can actually experimentally see from the angular resolved photoemission. And one gets these at the 6 Dirac points, you get the weights concentrated around that. And as you go from Dirac to semi-Dirac in the last picture, which is F, you see that it has vanished everywhere, and it has come to a point which is, between the 2 Dirac points, and there are weights concentrated at these 2 Dirac, as these 2 points, which are not the Dirac points. So you don't have Dirac electrons here, you have a semi-Dirac dispersion here, and these are, there's the Berry curvature. So I'm coming to the topology slowly. So I've calculated the Berry curvature, and finally, one gets a phase diagram. And one actually sees that as you turn on this deformation of the band, that is make the one of the hoppings to be different than the other two, the nice Halden phase gradually vanishes and will be completely equal to 0 at that semi-Dirac limit. And I've shown various regions. And again, just to remind you that this formula for the Chern number is analogous to the Gaussian curvature being integrated and getting some Euler-Poincare characteristics. Now we have integrated over the Brillouin zone. So this is a phase diagram. The phase diagram shows that the topological invariants are vanishing. And so would be, so if you calculate the Chern number, you see that there are topological phases when Chern number equal to 1, and then the Chern number will vanish and will give rise to a trivial phase. And we haven't broken any of the fundamental symmetries that protected the topological phases. So that's the interesting thing here. So finally, to come to the conductivity, the Hall conductivity, so to say, we have calculated the Hall conductivity for graphene and the semi-Dirac. And it turns out that this red line, bold red line on the top, is actually the anomalous Hall conductivity. Why it's called anomalous? Because there's no magnetic field. So you have a complex second neighbor hopping. So the anomalous Hall conductivity, which had a plateau at E square over H, completely goes to 0 in the semi-Dirac case, and so on. Okay, and so the Hall conductivity is vanishing, which means the topological invariant is vanishing as well. Let's go to another very interesting thing which has taken the world by storm when it was first proposed, and it's called as a Kane-Milli model. And these two people, Kane and Milli, Kane is the one on the right and Milli is on the left. So they got a prize called as a Science Breakthrough Prize. You might have heard about this, and it is considered to be as prestigious, if not more, from the Nobel Prize. And our very own Ashok Sen also got this Science Breakthrough Prize. And they got this prize for probably two reasons. One is that their brilliance in seeing the different symmetries of complicated Hamiltonians without really solving it. And then they, because of this relevance to the field of spintronics, which you might have heard of, where people are thinking of getting spintronic devices, where the spins would be allowed to carry the information rather than the electrons. And what's the big deal about it? The big deal is that spins do not undergo Joule heating. So you don't need to cool the system, which always you have a computer, and the computer always has a fan on. And if the fan doesn't start for some reason, fan goes bad, then the CPU also shuts down. Okay, and because it needs to cool. So there's no Joule heating for the spins. Spins do not interact with phonons and would give rise to damping and so on. So there'll be lossless transmission, very efficient. The sort of lifetime of electrons is very small, so you cannot make it carry over a large amount of time or span of time, whereas spins have very large lifetime, so that can carry information undissipated over a very large time. And so as I said, that two of the very important key ingredients that they could see, Kane and Milli, is that you bring in spin of electrons. Now, when you say that you bring in spin of electrons, you don't have to do anything much, because we know the electrons have spins anyway. So you include them in your Hamiltonian, and when you do that, this is what you get. You get a Hamiltonian which is exactly the same as Halden's Hamiltonian, but with a flux pi/2 for upspin and a flux minus pi/2 for downspin. The flux that I was talking about, the magnetic field that you would get because of this complex second neighbor hopping, it emulates having a up magnetic field at the center of the hexagon and down at the vertices of the hexagon. So the Kane-Milli model exactly becomes a Halden model, but now a 2x2 structure, one for the upspin and the downspin. And they actually saw that the time reversal symmetry, which was broken earlier, is now restored, is preserved. And this is one of the finest things that when I met Charlie Kane about 3-4 years back, this is what he's told me, that this is one of the nicest things that they understood just by looking at Halden Hamiltonian. But there is a second part of success to it. The second part of success is writing down this term, which is called as a Rashba spin orbit coupling. So which could be again inherent, just like spin, to two-dimensional systems. Because these kind of terms arise, spin orbit coupling, it's a hyperfine, not a hyperfine, but it's a perturbative effect in various systems. It's a hyperfine effect in cold atomic systems. But it's a fine structure effect, so which is nevertheless 1/137 times lower than the normal 13.6 electron volt for hydrogen atom, which take that as a benchmark. But the systems such as graphene in 2D is very likely to have this kind of term in the Hamiltonian, because you have surface inversion symmetry breaking. So the inversion symmetry is broken, in the Z direction, because it's just a two-dimensional surface and it's grown on a substrate. So something that's on top of that sheet, it doesn't match with something that's below. Okay, so that in those systems, this is something quite natural to have. And if you have that, then you have a sort of pictorially situation emerges that you have, instead of one edge modes, which we have shown earlier, there are two edge modes for each kind of spin. So it is like that, some special kind of highway where it is completely decoupled, and you have a red carrying the downspin in one direction and the blue carrying the up in the other direction on both the edges. And this is the time reversal symmetry is intact, unlike the Holden model. And the low energy Hamiltonian, it looks like some, I've written down something, but these are the tau z is the Dirac, the valleys of the Dirac cones. Sigma z is sublattice degree of freedom, and sz is actually spin. One doesn't have to really bother much about this. So one gets spin filtered edge states, which is what I had just shown. And the quantum now shows, the system now shows quantum spin Hall effect as opposed to normal charge Hall effect. Okay, so it's a Hall effect in the spin sector. And if you want to use these spins for carrying some information which is relevant to your system, then that's what is called as the spintronic applications. So Ken and Millie got this science breakthrough prize for actually unearthing this the fundamental symmetry, that is time reversal symmetry, being intact if you add spin, and also to add this spin orbit coupling in order to make it realizable for spintronic devices. And then you have a spin Hall conductance, which is given by 2e square by h, as opposed to e square by h, because of the presence of 2 spin degrees of freedom. Again, we go through the same thing, and one doesn't have to show that. In fact, first only see the first one and the last one. You see both have gaps, but they're not same kind of gaps. One is topological, one is trivial. Okay, and this is what we show again in a ribbon. You see the edge states for each one of the spins crossing, and the same kind of edge states, they actually merge with the bulk, and they are no longer topological insulator for the case of for the semi-Dirac case, and it's actually topological for the Dirac. So it's trivial for semi-Dirac and topological for Dirac. So this is what something that emerges in the nano ribbon. Same thing on the spin Hall conductivity. You again see that the plateau disappears, which is what it should, because the topological invariant disappears and so on. And we haven't defined what the topological invariant is, but there is a nice topological invariant called as a Z2 invariant. These are slightly harder to understand unless one really looks at all the tenfold symmetry classes of in condensed matter physics. So the Chern number is 0, but there is another topological invariant that emerges, and that's what gives this quantum spin Hall phase to be a name that is a second kind of topological phase. So there are only two known topological phases. One is because of the quantum Hall effect, and the other is because of this, the spin Hall effect. And again, the Z2 invariant, which is the topological invariant here in this particular case, because the Chern number is 0, because it's 1 plus 1 and minus 1. So the total Chern number is 0. But if you subtract them, then it becomes equal to 2, and this is what we get. So we get so this is divided by 2. Z2 is that the effective Chern number divided by 2. So mod 2 means you divide by 2 and so on and so forth. So this is equal to, it goes from 1 to 0 and from a topological to a trivial phase. And this is what has been. So you can actually destroy the spin Hall effect by going from a Dirac dispersion to a semi-Dirac dispersion. So that's a tunable. And this was the phase that Ken and Millie got, the red one. And then we have shown that this actually vanishes by the band tuning. And this topologic, so one undergoes a phase transition from a topological phase to a trivial phase, even here where time reversal symmetry is intact. Okay. So this lobe, which is where the topological invariant Z2 invariant is non-vanishing inside that inside these circles or the diamond-shaped structures or the ovals, and they become zero outside. So this lobe shrinks and gradually becomes zero at the semi-Dirac limit. So finally, what emerges is that if you compare between the two, where the time reversal symmetry is broken in the left, which is a quantum Hall system, and time reversal symmetry is intact, which is called as a quantum spin Hall system, the thing that emerges, or the scenario that emerges, is that there are edge modes in both. There are spin filtered edge modes, and there are these very important difference that in one of them we have explicitly broken down the time reversal invariance, and in other case it's intact, but both behave in the very similar manner under deformation. Okay, so that's the in short outcome. I'm running out of time as well. I have 5 minutes. I'll take 1 or 2 questions, or maybe any number of questions actually. So this is the first outcome, that we have been able to show topological phases emerging out without tampering with the fundamental symmetries of graphene, and works both in cases where the time reversal symmetry is broken and where it is intact. And as a special case, the spin Hall conductance, which is relevant for spintronic properties, can be tuned and even made to vanish if you deform the band structure. Okay, so thank you very much for your attention. This is the picture of IIT Guwahati. It's extremely scenic. When you get a chance, you're most welcome to visit. This is the lake that lies, it's called as a Serpentine Lake, which lies at the middle of the campus. Not so middle, but yes, it does. And the beauty of this lake is that it is actually fed, it's connected to the Brahmaputra, which lies on the left, and it's a huge one. And in fact, the physics department is right next to the river, so we can see the river from our offices and so on. And again, extending welcome to people who get a chance to visit. Thank you.
Okay. Thank you. Thank you, Professor Basu, for your very interesting and informative talk.
Thank you.
So, is there any question?
Yeah, yes, ma'am. I think Dr. Momita there has a question. So I guess so. I mean, it's from Momita. So she's asking, is there any link between Char number and the localization of states?
Say it again, please.
Is there any link between Char number and localization of states?
Very good question. A very good question. So, ma'am, I mean, it's a very good question, but the localization, yes, the localization would happen to the bulk of the material, yes. But to the edges, they are delocalized. So if you can selectively calculate, which is what people did when you, in fact, all these plots that I have shown are for a finite size system, which are called as ribbons. when we calculate them, their wave function, and take the mod square of that to calculate the probability, or calculate the current, which is a psi star del psi minus psi del psi star. The current is 0 for the ones which are inside, so they are localized, and the ones which are on the surface or which are on the edges, they are conducting. Yes, so there is a nice connection. So churn number, the value of the churn number will say how many edge modes you have.
Because that actually depicts the quality of the topological insulator, right?
Yes, 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 it does.
Thank you, sir.
Yes, thank you.
Any question more, Thomas?
I don't see any other questions. I don't see any other questions. So participants, if you have any questions, you can.
Yeah.
Or ma'am, if you have any questions, you can ask also. In the meantime, I mean, please ask.
Yeah, I just want to know, just for my knowledge, the quantum Hall effect is about 2 dimension, right? So
yes.
Can we extend it to higher dimension?
Oh, very good, very good, very good. Yes, there are, the way I have presented it, it looks like that the quantum Hall effect is very specific to 2 dimension, and but it is actually not. There are 3D realizations of quantum Hall effect as well, where exactly the thing that happens in 2D gets carried over to 3D, where the charges that segregate the positive and the negative charges, they accumulate on the surface rather than at the edges. So there is a definite this thing at the realization in 3D as well, and a lot of people work on 3D Hall effect, quantum Hall effect in 3 dimension. Yes, so there is.
And also on some fractional quantum Hall effect.
Fractional quantum Hall effect. That's another talk maybe sometime. See, this is a very interesting thing that people have gotten fractional plateaus at the fractional this thing. So if I show my all these, one of those things that I've shown earlier. Here.
Yeah.
That's the one. So here you see fractional, rational fractions like 1/3, 2/5, 3/7, and so on. So there are about 100 fractions being seen, and sometimes there are improper fractions also, like 11/4 is an improper fraction where the numerator is more, and so on. There the physics is very different. They're still Landau levels. But these Landau levels, because of the enormous number of electrons there is the interactions had to be brought into picture. So electron-electron interactions have to be there, and they play that's the only energy scale left in the problem. Whereas integer quantum Hall effect, you can understand in a non-interacting picture. Okay, but it's the same Hall effect, but it's a hierarchy of energy scales. So if you have the magnetic energy to be very large, and then the interaction energy, and then the sort of the tight binding energy, and that is the regime where you have this fractional quantum Hall effect. Very interesting, and in fact, one of the Indians have contributed a lot to this. His name is Jeetendra Jain. So he wrote down a composite fermion wave function where an electron actually carries a number of flux quantum, integer number of flux quantum, and that he wrote down a wave function which could be, if you do a variational theory on that, you get all these plateaus, or at least the fractions that one obtains. And very nice work there. So it's a very nice topic, but we're not talking about it because we don't have interactions we are fully on the tight binding limit.
Yeah, I have seen that paper actually.
Composite fermions. Yes.
Thank you so much for your nice answer. If there is no question, let us thank the speaker. for his time. Thank you so much, sir, for your valuable time to us. And as usual, we are looking forward to see you in the campus physically.
Absolutely, absolutely. It'll be a pleasure. It'll be a pleasure. Yes.
We will have the
Yes, sir.
campus. Beautiful campus.
Yes. Sure.
Thank you.
Thank you very much.
So let us, Dr. Mukherjee, let us end this session, right?
Yeah, so we are going to take a lunch break from 1, so up to 2:30 is our scheduled lunch break, and then we will continue with our invited lecture session. But in the meantime, I would like to say that those participants, if you want the participation certificate, then you will be contacted over email from the organizers, and the students who are present here and want participation certificate, you can write to Dr. Papia Dhara, and her email address is given in the chat box. Please refer to that email, and if you write her with all the details, you can get your participation certificate. But provided you have participated both the first day and second day of the seminar. And so, is there anything to mention, Dr. Momita? Please, you can.
No, Tamal, it's absolutely okay, because for the participation certificates, we will send them after participation, after their contributed talk session. And for the presenter certificate, and for the participation certificate, they will receive a feedback link over mail. If they don't receive, some of them miss the link or don't receive the link, they can write to Papia or Dr. Shodrupa. I'm providing both the email ID here.
Okay, then let us conclude this session and let us go for a lunch break. And please reassemble at 2:30. Okay. Thank you all.
Thank you,
everyone.
Thank you. Should we leave meeting now, Momita? আমরা কি লিভ করে যাব?
না ম্যাম, আমরা এখানে লগইন করেই থাকছি। সবাই লিভ করে গেলে লিংকটা অসুবিধা হবে, because we will use the same link.
Okay.